Okay, we are recording. Good morning, this Friday, 22 of May. So today's class is gonna be kind of not a master class, but more on how was made, the TV program, on how they make things. So actually it's gonna be something more similar to that. And actually how the CNC by the sea, the project that we worked yesterday, was done. Just to clarify for the recording, what is the so right now in the lab we have a custom CNC machine that all the students are controlling remotely, and so they can send through this interface, kind of front interface or Repetier web interface, and they can see what they are doing actually with the cameras. I don't know which one, but you have the cleaning tool down, so be careful with it. Don't put the Z too low. So let's see first what the students think and they understand about this machine. I want to open an open question on actually what you guys think and how you think we build this machine in the overall, like hardware, software, how we are connecting. So any of you want to take the lead and kind of explain what you think you are doing? Don't speak everybody at the same time, please.
Oh, maybe from what I know, I guess that the Raspberry Pi is the Nexus point that is open to the internet and we access it. And from the Raspberry Pi, we access to the Arduino, whichever board controls the CNC. I don't know which is the parameters of that connection. And the CNC, the Arduino in the CNC is which has the control of the machining tool. This is my guess.
What was the question?
How this project
was made,
basically. There are some little like men inside the machine. Actually, there is an instructor hidden just behind the camera controlling everything in live, sending your live commands. Or are you really controlling it through online?
Can I try?
Can you try to explain?
Hello?
Yes, please.
So I think the CNC machine itself, it has like 3 axes, right? X, Y, and Z, and each of them are connected to a board that controls that particular motor to move in that direction. And then all of those 3 boards, they connect to one single board, which you connect to the Raspberry Pi. And the Raspberry Pi acts as a computer because it's connected to servers or IPs, and the IP connects to the application, which is browser based, and the application helps accept G code and sends it to the Raspberry Pi so that the G code is converted to the movement of the 3 motors. And I don't know how the application itself is, whether it's like a ready thing or something that is made specifically. And then there are these cameras that connect to the console of the browser through a particular IP. Yeah, I guess.
Actually, quite close, yeah. Benjamin?
No, I was going to say, it's quite a vague question. Like, do you expect us to talk about what kind of protocol was used to send the data? Or like,
I don't know, like, it's open question.
Yeah.
You can try.
I don't I see the Kraken. I don't know what it is. The Kraken, what it means.
Kraken is how we call actually that machine, because the Kraken is like the mythical, like marine monster that can grab everything and is huge. So actually this machine was designed to grab kind of anything or whatever and to grab everything, like one to rule them all. Multi-purpose machine, so we just call it for fun cracking.
I think Vitali said it all.
Okay. So
no, I think I'm closer to Mitali, and maybe an analogy would be that it works as a printer. So if you send data like to the printer through the internet, then the printer does whatever you ask it to do. So it could be like something of the kind of like a Arduino that is connected to the machine. So it receives certain data and it just executes it.
yeah, actually, let's say it's a custom built machine, but uses kind of all the standards for like machine control. So let's start with the part that I'm, of course, more familiar, and that is the hardware one, and more or less on the machine control. So in the lab right now, you have a machine that someone is hitting something actually right now.
Oh.
Guys, don't break it. Actually, the machine right now is stuck.
I think it's humping the piece of plastic.
Yeah, because you are not, because you try to make the origin with the tool down. So actually it cannot hit the Y end stop, and it's just trying to bounce back again, and it will do it endlessly unless we stop it. So let me try to refresh it, and please stop. Fuck.
You know what happened to me yesterday? Because it was happening that too. I figured it out actually because the camera was moving from one side to other and like bumping. And
guys, be careful with the probe. If you are feel not confident with the servo motor, please don't try not to use it.
And
Yeah, it's my fault. It's my fault. It's my fault.
Like the servo is not a Metal Gear servo, so probably will break down if you keep doing these kind of things.
Where do you have the other camera? Because I only have the camera from the top.
Okay, we'll put it in the chat.
Thank you very much.
This is one of the cameras, and this is the other camera. Okay. Be really careful with the probe. Okay. I just would like to ask you that. No problem if you break it again, but you will not be able to use that utility because we are not coming back onto the lab until Tuesday.
sorry, which was the code to level up the servo?
I wrote it down.
Yeah, but wait. No, I wanted to ask you. I don't know if you already did it. If you did, sorry. If you could explain us after which are the initial commands for the cleaning code and the final commands of the cleaning code, like the M1s or G90.
Okay, I think I have the cleaning code around here.
And I was seeing something also. I don't know if it happens to you all, that the command G21, which is set it into metric. It is not recognizing it.
It says because the machine is forced to actually go to metric, so it says it doesn't recognize it, but it's recognizing it. So
Okay.
don't trust exactly.
Okay.
So okay, let's go a little bit into the G code. So first we set up everything. This is commented, like the machines ignore it. If you put a space, it will probably could kind of sometimes work, sometimes not. So try to avoid spaces. So the machine will jump into metric mode. After, we will put the machine in absolute coordinates. G91 is relative coordinates. Marlin is not a system especially designed for it. We will explain what is Marlin later.
Sorry,
we will
what is absolute coordinates?
Absolute coordinates. Here, this is the 0, 0 of the machine.
Okay.
So that means the reference point for the 0 is the 0 of the machine. It means the mechanical end stops, the limits. So you remember, for example, in the CNC, you can make the 0 here, like the SRM for the PCBs. You can do it whatever you want. That is relative coordinates. So you have a main absolute coordinate that is the machine limits, and you can set up a new origin. That will be relative coordinates.
Absolute.
So the relative coordinates would be the minimum possible x and y and
Exactly.
okay.
Well, relative or absolute would be the minimum.
Absolute will be like the minimum
Physical.
x and I and z of the machine.
Yeah.
Okay.
In this case, the machine has the limit is on the positive, so actually is slightly different. But the x and y, yes. So we have G28 that is actually make home. It means find what is the absolute point. We have this that is a G code that actually will put this in the screen.
For G28, does it do like home in order, like home to X, home to Y, home to Z?
That you can configure it through the firmware of the machine. Right now is actually first level the Z up, because if not you will touch. Level 10, 20 millimeters, and after you have moved it up, even it doesn't know what it is, so it will move it up whatever position it is. It will after that move the X, bounce 2 times to confirm the accuracy of the position, and after it will move the Y, bounce 2 times. When that is finished, it will slowly plunge the Z and deploy the probe at the same time. So it will touch, go up, take back the probe, put it back again, and touch again. So it has a double confirmation of the limits. So we have home, we have sent this screen message. Actually, it's just for aesthetics. It's just to show on the LCD screen of the machine. Right now, you cannot see it.
Sorry,
And
another question.
Edu,
yes,
When you said the G28 in G coding or in another machine, it's always the same, or you have to declare what G28 is gonna mean? Like, I don't know which is gonna be my set axis, or
no, actually the G28 is the most standard command of G codes and NC codes.
but
Like,
you need to declare what's the home for you, don't you?
no, we don't declare it. We tell the machine to find the machine limits, the hardware limits.
Okay.
And can you override them?
The machine limits.
No, not the limits, but I mean, like, what if
The
I want
origin.
to have the origin in the middle of the machine?
Okay, in that case, let's say, for example, you want to make the origin in the middle of the machine. What you will do is move, for example, the middle of the machine is, let's say, 500, why 500?
Mm-hmm.
We don't want to change the Z. So
Z.
after that, you will send a G91.
Okay.
That is,
And yeah.
that is actually use relative mode. But in relative mode, you don't only need to send G91. You need to set up the origin. And actually, it's in Marlin doesn't especially like these kind of things and might become a little bit buggy. So that's why we don't do it. So G-code Marlin, relative coordinates, relative positioning. Yeah. So G91, set all axes to relative. Yeah.
This is like when we have the bigger laser machine that we have to set this several homes.
Exactly. This is what you do. You are sending a relative homing position.
And I mean, like, can you explain further the difference between Marlin, Smoothie,
Yeah.
Tanky?
But yeah, I'm going to this, but you asked me this question.
Okay, sorry.
So let's finish with explanation of this and we will go through all these kind of things. So the next layer is actually move to a position. Is move fast to X30, Y750, Z90 at this speed. So what we are doing is don't stay here, but move here a little bit into the sun. And we are moving really high because we want to move the probe down. So we have moved to this position, but the probe is still not deployed. Actually, I can do it in live with you.
Please do.
Shut up. So actually, I can send this line I need to write it. Ah. Sorry, too many things open. I don't know if you can see anything.
Yes.
Okay. G0, X30, Y 750, Z 90, F 5000. So actually it will not unknown command. Why? What? Okay, let's just send that G1. Do I made any error in the syntax?
It doesn't seem.
Okay. So it's moving to that position. What we need to do now is deploy the cleaning. The cleaning, we do it with a servo command. That is the
M400?
M280 P1. M200 is in servo move. P1 is servo 1 because you have servo 0, servo 1, servo 2, servo 3. I have it connected to servo 1 to angle 0. Okay.
Wait,
If
so
you-
so everything that it's M, it's a servo command?
It's a servo command, yes. So for example, I can also set up S45. It will set up at 45 degrees. M280 P1 is S90. You can even move further. I will not move really much further because I don't know if we're gonna hit. Actually, it doesn't allow it.
P
So-
number of servo?
I think your video that we can see like in the screen, there's some windows blocking the way because I think maybe it's us.
It's Zoom usually.
Yeah, it's Zoom, but like Zoom is in the way.
Yeah, sorry, and there's so many things. I don't have my second screen today. Okay, so the prop is down. Now what we need to do? Move down, no? G1, the same position that we are right now. X30, Y 750, Z. I will put 70 just in case. And now you can start cleaning. Let's say now you're in touching the sand and you can start cleaning. What the command M400 is? Actually, is something that is quite silly, but not that silly, in fact. You know that the machine is reading the commands, no? It reads this command and theoretically, it should, when it finishes this command, it will do this one, no? It will do one by one. One. What is happening? The machine, let's say, preloads. I think I have set it up to preload like 12 commands in the memory. So the machine has always 12 commands waiting in the inner memory. What is happening is when the machine does this command, the microcontroller has sent these equivalents to the motors. So actually, it will, to the motors have a motor driver. That is another microcontroller that controls the amount of movement of the motor, no? So for example, this, I know that this machine has a demultiplier of more or less 100. So it will say axis 1, move 300. Axis 2, move this. And axis 3, move this, and all at F3000 speed. So let's say the I want to draw how I can draw annotate. No, I want to new share whiteboard. So we have the let's call it Arduino. Could be an Arduino or not. We have the motor driver and we have the motors. So this, as we have a 3-axis machine, we have 3 that they are connected to the motors. So when this process, the first instruction, deconstructs it and sends the instructions to these guys. But these guys, they are executing the instructions, but they take time. And time is a constraint here. What is the constraint of the time? One is the mechatronics of the machine, how fast it can accelerate, the maximum speed that is doing the command. So what is happening? That here, where we have set up this instruction, the machine has sent the first line, and it will this one has finished to read this line, it will jump into the next one. And it will send at the second one. What is happening here? That we read this one, we have already sent to execute to the drivers, and the next instruction is this one, and after this one, and we do this really, really fast. So what's happened? This instruction, the real execution time could be around 2 seconds. It's the time for the machine to move from one position to the other position. But this instruction is really fast because it's not one of the motors. The motors are still executing instruction number 1, but this guy is already processing instruction number 2. What happened? That the instruction number 2 is another thing, like the servo. So what can happen is instruction number 2 can be done faster than actually the final position of instruction number 1. You understand that? Hello?
Not very much, because the internet is quite difficult to follow.
Okay, I will try to change my network.
Yeah, I don't know if you also see it, Edu, but you have like drop frames.
No, for me you are okay. Okay, I will. Maybe I can disconnect the IP cameras also.
But I think, Edu, is the different parts of Zoom that are getting on the way.
Yeah,
that
and
they
Zoom
don't
is
show.
auto-blotting.
Okay, let me see.
Should you did see?
Just before we break anything, I want to be sure. Can you tell me if the probe is up or down? Guys?
Yes, it is down.
Yeah, it seems to be up.
It's deployed.
I think it's up.
Okay. I will just
I think
keep
it's
it.
up.
No, it's deployed. Now it's
Okay.
Up.
Okay, just in case I want to close that before anybody gets into control of the machine. Okay, do you hear me well now? Better?
Yeah.
Yes.
I guess.
It's not hearing. Is when you share your screen, we see like a blue background with lines.
Yeah, glitches. Lots of glitches in your background. So it's
Can you
Just
see
hi.
this now?
We see the whiteboard.
Yes. Okay, so I will start again.
It was such a beautiful
And
drawing.
again, the blue things.
No, guys, but the black with stripes, it's Zoom or any other application that it's blocking sharing. That's not internet, right?
Yeah. Like at bottom is just probably the window where he sees all of us.
Yeah, it's Zoom.
And at the top, no idea.
Okay, we'll make you even smaller.
Here we are, even smaller.
You are like 1 centimeter right now.
1 centimeter too much.
I think it's better now.
Okay, so these are the motor drivers, and the motor drivers are connected to the motors.
Are you gonna make the independency flag?
Yes. And this is the servo, okay?
Perfect.
Okay.
This is the last part of the pelada.
So, so this guy is reading instructions. 1, 2, 3, 4. So let's take the first one. We read the first instruction. This one transforms the G code into instructions for the drivers. So it's stating to this guy, instruction number 1. And this one has a constraint of different things. Speed, acceleration, sorry for the writing, and time. So when you send a command, this is done usually like 0.01 seconds, like super fast. But this, the translation of how many turns we need to do for the motor is not that fast. This could take like at least usually at least 1 second, depends on the amount of movement that you're deploying. So what happened? This one has already sent instruction number 1 to all of them. So this one is not doing anything. So what it will do? It will read instruction number 2. These ones are busy, but instruction number 2 in this case is move the servo. It's not sending anything to these guys. Can you hear me? I don't know. Sorry.
Yes, we're
Yeah,
listening.
yeah,
Okay.
yeah, we
Yeah,
can
good.
hear you.
Okay.
Yes.
So this guy, this instruction is the servo. These guys are busy doing it, and this guy is not. This guy knows, but this one is free, so it will send the command number 2. What is happening? That if you make a timeline, this guy has to reach this position. Is on his way traveling, and this can do the command, let's say, much faster, because we can speed it up this acts much faster. So theoretically, number 2 has to be executed after when this one has finished. It means here. What happened? This one can do it faster, so it will execute it here in the time, just a little bit like sooner than expected, and that's a problem. Why that's a problem?
Because maybe you haven't already put it in the height, or I don't know if you're gonna lower the cleaner part and you haven't gone high enough.
Yeah, it's not set on the right position yet.
Exactly, you are not in the right position. So what happened? We are moving from this position to this position, and in the meanwhile, we don't load the probe. What can happen? We can hit a lot of things. We can break the machine. So we need to introduce a command that is not wait, but finish completely the command until you do the next one. That is M400 command. M400 command is actually finish moves.
So it's sort of the relation. I don't know. I know that maybe it's not the same, but between delay and millis, like stopping.
It's not a delay.
Yeah, no, but I mean it's like stopping, doing 1, doing 2, doing 3, and not being able to multitask. Like stopping the multitask function. No?
No, is the machine has to do a movement. In the firmware, we have set up the speed and acceleration, and we know the amount of movement. So the firmware, the Arduino can calculate that this movement will take 2 seconds. So it will a way to do it is it will not load the next command until we have spent 2 seconds, so we are sure that we are in this position. And then it will execute command number 2, the next one, like the following command. that in this case is command of the servo. So M400 is a command that says finish moves, and it will calculate the time that the machine will take from move from what position from the origin, that we are in origin, to this one. It will calculate the time based on the acceleration and the speed. When we have done finished this command, because we have waited time to finish this command based on the acceleration and speed, we can then execute this one.
But I thought it was always the case with the G code, like always the command launched one by one and in queue.
That it does when you have is like that when you have commands like this, because we are activating, let's say, the same access. So of course it cannot send this command until it finishes this one.
Okay, that's a memory on a specific mother.
Exactly.
Not on, okay.
What happened here is like we are in here, we are activating access 1, 2, and 3, but this is, let's say, the 4 active actuator. This one is not doing anything, so it can preload something into this one. And this one, because of the characteristics of itself, this servo is super fast. It will do it faster than actually finish the position of this one. Meanwhile, if you just are sending X, Y, and Z commands, it will not load these ones until this one has finished, because this actuator is busy doing something. Until this one is free, it will not send the next one. Thus, because they are the same access, but this one is a different access that is free to do things. So that's why you need to use this kind of commands. When you are sending an instruction of a different tool or access that you were not using before. Actually, there is something that is really similar, but it's not done like that. It's not doing by internal calculations. It's dwell. That Pablo, this is actually a delay. So G4 is dwell. It means wait or pause everything for X amount of seconds or milliseconds.
And what does it mean when it says precedence?
Sorry?
It says if both S and P are included, S takes precedence. So I mean, like in your code, you have a P.
10 seconds, yeah.
So I guess you are using the M400 and also the P as for dwell, right?
No. You cannot. No? These are different commands. M400 is a command by itself. You cannot set more instructions. But let's say in the middle of G code, we want to wait. M400 is not going to be useful, because if the code is executed, it will jump into the next one. No? Let's say we want to pause the machine. Just pause the machine. So actually, we will set up a command G4. In this case, we will use seconds, for example.
But I think what S takes precedence, if you put G4, S5, and P50, it's going to read S, not P.
Yeah, I think so. I think so, Benjamin.
Yeah, that's what it means. Takes precedence. So it's basically if you've put both, it's not going to use both. It's just going to use one of them, and it's going to be S.
It's like a priority.
Yeah. So G4 S5, it means when you have reached this position, stop the machine for 5 seconds. When do you want to do this kind of commands? That's interesting. What happened with the motors of, for example, the spindle of the machine? A machine takes time to switch it on, no? A spindle, you can switch on the spindle of the motor of a CNC cutter, but it doesn't accelerate instantly. It takes like 1 or 2 seconds to completely get the full revolutions, no? So actually, those commands are, for example, to, I want to wait for 3 seconds, so I'm pretty sure that the motor is completely at full speed, because the motor can also takes time to accelerate. But the motor acceleration is something that we cannot measure. Like, we have to do it by the data sheet. When you buy a spindle motor for a CNC, they say from 0 to 22,000 RPM in 1.5 seconds. So actually, you will insert a command of 2 seconds just to be sure that the motor speed is at the speed it should be. Is for actuators that we cannot control the status, but we can do it through time. Yes?
Yeah. And
Okay.
It's not possible to have a feedback to.
That is mechatronics. Actually, that's next week. Is closed loop versus open loop control. So, okay.
What do you mean with feedback?
To know exactly what status is the machine, which position, where is everything.
Refresh the page.
Refresh the page, refreshing page.
Edu, could we, I don't know, since we have X, Y, and Z axis, can I set different speeds for them? For example, in X and Y at 5,000 and Z at 3,000, but in the same time?
In the same line, no.
Okay.
There is no problem to do this. Actually, it will read this as a one command.
Since you are not using the same actuators at the same time.
Exactly.
Okay.
That's the point. You need to understand this. Like, you are not activating the same thing the same thing. So actually, you can move these 3 lines. It will load one super fast, and it will send each one differently. So actually, in the real world, like, the difference in movement between this and this, let's say on how it activates the 3-axis, is about like milliseconds, not even. This is going to be mainly based on what is the clock speed of your command controller. Yes? Okay. So in the Fab Lab, we have the Kraken machine. The Kraken machine has a 3-axis and a servo. There we have.
Very quickly, just if you view the image, is like 400 dpi, so you can zoom in if you want. If you click on it and just zoom.
Ooh, fancy resolution. So we have the Kraken motors. Oops.
Can you put the link of this page? Because I have a problem with Edu's.
So we have the machine. The machine has some motors, motor drivers, and the control board. This is a machine by itself. Let's say it could be, in this case, is a Kraken, could be a 3D printer, could be a CNC, could be a laser cutter. Usually, you are used to control it by an SD card or a USB connection to the computer. In these cases, what you are reading is actually a G code from an SD card. The SD card reader that the machine has actually is a kind of SPI interface that is kind of similar to the USB connection that basically is reading the code. So we can, in a really like broad point of view, we can say that basically we have a serial connection to be reading G-code commands. So what this connection basically is inputting and outputting G-code commands. Go back and forth, sometimes only back, sometimes also forth. Because we, in this case, for example, when you, the CNC by the C, if I open it here, if I click G1 Z15, is saying, okay, no, So that will be a command that the Marlin is confirming that it has read the instruction properly. So I'm sending the G1 C15 and sending back, okay, I received the command. So it's a confirmation communication dialog. Super simple, actually. In the other part, we have what? We have actually a Raspberry Pi that has connected to webcams. Those webcams, we are actually using them as an IP camera. An IP camera is basically a web stream that you are just publishing an IP address. And we have the CNC that I'm not sure because Oscar did this part, but it's pretty similar to Node.js, no? I'm wrong, Oscar?
It's an application written in Node, yeah, that basically makes a front end to control the machine, but it runs in Node, yeah.
So
how do you connect two cameras to the Raspberry Pi if it only has one camera connector?
With USB. The Raspberry Pi,
webcams.
They're normal webcams.
Ah, USB cam, not Raspberry. Oh, okay, thank you.
So in, let's say, one stream, we are sending two IP cameras. We are producing two IPs that are actually, this is one, to access the webcam streaming that is processed by the Pi. That's why, since yesterday that we connected the second camera, sometimes it freezes a little bit because it needs to do so many things. In the Pi, actually, we are assembling a GS interface that is this one. Actually, this is a kind of Raspberry Pi version of what it could be Repetier. Repetier is, amongst other programs, is a control interface of a machine. Actually, it looks similar, but if I go here, manual control, you see, startup look really similar. We have the workspace of the machine, we have a connection dialog, and we have some moving commands that this, when I click, is just sending a standard like G1X move 10 millimeters, for example. And we can control different things. And in this part, for example, we will connect and see the G codes. So this is kind of a control interface. It's not more than that. It's a visual way of communicating to the machine instead of using straight G codes. But if we could access actually the machine just by black screen command line to communicate the firmware, the Marlin, the machine, the Kraken in this case, we could be able to use this as a bridge. What we have done, actually Oscar has done, is assemble this interface that kind of makes everything smooth and makes everything easy to control because help us to deploy a camera, tell us the time, it tells us the time that we have spent, etc. We can upload a full G code, so a kind of automatize that we don't need to send each line of command on our own. Here, the port part is actually the connection. We need to set up what is the main connection and how we are connecting to the machine. So in this case, we are using the port USB 0 of the Pi, and we are telling the Raspberry Pi through the NCGS interface that we need to communicate at 250,000 baud rate speed. So we have everything here. And right now we are in the building. Let's say we are in the same network. What happened then?
What is the protocol you use to communicate?
Serial to the machine?
Serial, okay.
Yeah, it's serial communication.
Okay, thanks.
Actually, we have the Pi connected with a USB cable to the USB cable of the Arduino, straightforward. Like the standard Marlin RAMs board. You know that machines have the, can I see a three-dimensional view? Yeah. All the machines have this kind of USB-A connector. We have a USB-A to USB I don't know what's called B, for the Raspberry Pi. Straightforward. So actually the hardware connection between those is ultra simple. It's the same as you will connect. Instead of connecting to a computer, you are connecting to a Pi. So in here, we are in the Wi-Fi network. You know that have interconnections through the same network is easy because there is safety, but you can do like direct IP connection through the same routers. What's happened is we are connecting the IAC Wi-Fi or wire connection. It really doesn't matter. You're in the same network. So what happened? We are connecting through the servers of IAC to the main, let's say, outside world. So what happened is we need to leave a port. A port basically is a IP that we are able to send in and out with less security. Actually, I think Oscar can explain this part much better than me. But basically, we need to leave a kind of door so we can enter in and enter out. And this usually is not done in all the routers and modems by default, because obviously you don't want that people can enter into your house network, for example. You don't want that someone random goes through the port of your router and enters your network, so it can actually see everything that is connected and control everything. So yesterday, 2 days ago, Oscar was opening a port in the modem router, actually the server of the IAC, to be able to communicate remotely. So actually we can send information back without actually being there. What you are doing from home is you have your laptop connector to your router that is connecting to internet through the port that we have assignated into the server. You know that when you click Google, this is just a domain. Actually, what you are doing, this is just a random number, but you are connecting to something like this, a kind of cell phone number. This is actually the port connection of the whatever browser Google is using. Probably will use multiple of these and etc. So here we can actually see we could buy a domain from a domain provider that it will do it. It will translate this into a fancy name, CNC by the C webcam.org, for example. But basically what we are just stating is a equivalence. When we click into this address, we are actually going through this IP, but it's hidden for us. So it's easier for most of the people. Do you want to?
Sorry, do you need for that to buy like a domain?
Yes, from a domain provider.
And then you mask the IP with the domain name.
Really, Benjamin?
Fuck.
So Oscar, do you want to explain this part better, like the connection?
Yeah. So I'm gonna take over. I'm changing a little bit this drawing so that it's a little bit clearer. Stop to share. Do you see my screen?
Yes.
Yeah. Yeah.
So let me just reduce this. Okay. It was just, as you can see, this is like
sorry, Oscar, which software are you using to draw that?
It's an online service called Draw.io.
Wow, it's super nice, Oscar.
Yeah, it looks cool.
It's an open.
You didn't tell us. Like this is your hidden. It's only for you. Wow.
It's well, it's very simple. They have like I use it a lot to make diagrams for whatever, and it didn't take that long to make this thing. It's like
Oh
30
my
minutes.
God, it's so nice.
You have just changed my life.
Completely.
They have this thing of now these 3D things that is more like for server stuff, like Amazon Web Server icons that I'm using there. Like it's their infrastructure things, but I'm using them to just simplify the different parts. I think it's very easy to use.
It has even buildings. We can do a small architecture plan with it.
Okay.
Lovely.
Okay, so let's imagine that these two web cameras, I didn't put the drawings yet, but let's imagine that these two web cameras are connected here to the ports of the Raspberry Pi. Okay, so how is this working? From Guillem's class, you remember that each of the, let's say each of the machines that is connected to the internet, they have what we call an IP address. The IP address can be in two forms, like IPv4, which is the normal ones that you already know, that have the same as, for example, this one, with 91, 126, whatever. And there's also like now a new change in the IP into IPv6, which we're gonna start seeing new addresses that have more, let's say, more possibilities, because we have so many machines connected to the internet that now we have like a lack of IP addresses, okay? But nevertheless, what we see here is that in the FabLab building, we have, in the entrance, we have, let's say, some routers. And here, let's say this is our gateway to the internet for everyone that is connected under this network. This happens the same in your homes. So each of you have a small local network at home, which a router, and you are connected to your computer, to the internet through that gateway. In what we would call the local area network, okay? Each of these routers have, in the internet, this is like, imagine that this is like the outer world or the internet in general. Each of these have one IP, dynamic or static, that is assigned by the internet service provider, Telefonica, Vodafone, or something, and is somehow the way that we use to find each other on the internet. Now, each of you inside of here have a local IP, which is assigned by this router, and is telling the traffic that comes from outside to your IP, to this router, to which user each of the users connected inside should go. There are two ways. So as you see, sorry, there are always these gateways in the middle that somehow control the traffic between your computer and the outer world. How can you expose your machine, as we did the other day, to the outer world? You have two ways. The first way is that if you're at home, and we did this 2-3 weeks ago with the Node-RED, when I was here in my place, I don't have a server or anything, or sorry, I don't have an enterprise router or nothing like that. And I don't have one static IP that doesn't change. It's the IP of my router that is assigned by Telefonica in this case. How do I expose my Raspberry Pi so that you can send things from it, from your homes to the Raspberry Pi? With a technique called port forwarding. Port forwarding is basically taking the requests that come from the internet in a port, for example, the port 80, which is the HTTP port. You know that a port is just a door. It's just a door that has a number, and that way we are able to identify which protocol is going in each of them. So it redirects each of the requests that come from that door to my Raspberry Pi in this case by opening a direct connection directly to it. Does that expose any vulnerabilities? Yes. And that's why this time when we did it for the CNC, we tried to make it a little bit safer, and I'm gonna go through that. Okay. So that is, let's say, the first way. We have the IP of the router, and we just make let's say a tunnel that goes from the outer world to the computer using the technique port forwarding. You can do this easily, and probably some of you have already done it if you use like online gaming services or platforms that need access to your computer, for example, Steam or Unreal or these things. They tell you, okay, go to your router and do a port forwarding to the machine, the PlayStation, or whatever else. I don't use them, but I know that people do this. And it's basically a way for exposing a machine to the outer world. But that somehow is a little unsafe. So what we did this last time is that we built in the Raspberry Pi, in this computer, what we called a reverse proxy server. That is basically a little program, a little script that is running in the Raspberry Pi that is taking all the connections that come from the outer world, in this case in the port 443, but it could be in the port 80. So 443 is secure HTTP, port 80 is HTTP, just a bare HTTP, and the only difference is that there in 443 there's an encryption end-to-end with what we call a certificate. A certificate is a way that tell the internet that your connection is encrypted, and so that other people can trust it and send compromised data through it. For example, sending passwords, sending emails, sending things that are private. You should do it always in secure and encrypted connections. That's why in here you see this little icon, basically says secure connection verified by Cloudflare. So Cloudflare has a lot of certificates and they know which ones are secure or not, and they tell us if they are good to go or not. When you go in here, you see this little warning that says are not secure, such parts of this are not secure because we have HTTP stuff. For example, this camera feed in here. Okay, this is not sent in a secure way, but the rest is. Okay, so how are we doing this? This part, this is a program in a Raspberry Pi that is run by a script or an application called NGNX. What is NGNX? NGNX is a server application that basically turns a machine into, or is able to run and make, and turn over a machine into a server. This, let me go to the docs, is one of the ways that you can use to share content with the internet in somehow a secure way. You can serve many things here. You can serve static content, like for example, a website. You can host it using NGNX in your computer. And whenever I receive, or that computer receive a request for the website, it will deliver it and just send an HTML file as Guillem was doing 2 weeks ago in the terminal that he received the HTML file.
Is it something similar to Apache?
Sorry?
Is it something similar to Apache?
Yeah, exactly. So Apache is another way of, is another Apache server or NGNX.
And what's MQTT? Because we've been using it, but I don't really know if it's like the same to create a server in your computer.
No, not really. MQTT is a protocol to send data somehow in an organized way. But what would be the analog of the server in this case is what we call the MQTT broker, which is yet another script that talks MQTT and is able to receive messages from clients. For example, let me show you. Here, if you go to the FabLab VCN projects repository, here, so you see that we have, let's say, what would be the analog, the analog part of this, or the same part of the, as the server would be the MQTT broker that basically receives messages from people that are publishing data, sensor data, or whatever else, and sending them to subscribers. Subscribers are optional, let's say, so you can subscribe as a, it can be many things, like for example, a phone, or it can be a server in which you are storing the data, or it could be another computer to visualize it, or even a website. But basically what this guy is doing is just handling, is like a router of all these communications somehow. And this is somehow a server, but it's not a server, it's what we call a broker, because the only thing that it's doing is redirecting traffic and having somehow some persistence in the server so that you can store the data and not lose it.
And it's a bidirectional communication. It can send from one side to the other and from the other backwards.
So subscribers can't send anything, but the same device can be both subscriber and publisher.
Okay.
So this same device could have also, with the same hardware and everything, the software to publish, but the idea is that the subscriber is, let's say, like an abstract interpretation of a device that is just receiving data, and a publisher is a device that is sending data. But that those two devices could be the same or could be different. Okay. So what we were doing here, basically, is we were running this NGINX server, but in order to secure the connection, we were only listening to requests in the 443 port, so the HTTPS port. And inside the Raspberry Pi, we could have things that are somehow unprotected, running in HTTP, but that are hidden to the outer world, and people cannot mess around with them, because in here we also have a login in it. And basically people that want to access to the Raspberry Pi, they only have this way using the 443. And these agents, let's say, is handling all those connections and only allowing the 443 connections and doing something that we call a reverse proxy. What is a proxy? A proxy proxy is basically a small, it can be a machine, it can be a script, just a program that is making a bridge between two processes or computers. In this case, this proxy, what it's doing is connecting the application of CNC.js that is running inside the Raspberry Pi and is sending data in port 8000. So when you run CNC.js, it will do something like open in like this, port 8000. This is 127.0.0.1 is normally local host. So it's the machine itself that is serving content to itself in one of these doors. You choose whichever port you want. This is where you will be able to, so,
I wanted to ask you also that localhost, it's the machine, not the Wi-Fi router. It's not the main.
No, exactly. is the same, is the machine itself. And localhost, so when I write here, local host,
it's the same as 127.0.0.1.
exactly, and that is my machine. And if my machine is serving something in port 8000, then I will be able to access it. For example, if I have a device in the network, for example, my router, that is normally the number one in the local network. The local networks are normally 192, 168, and then 2 more numbers. Here, I will see my local router. This is the Telefonica router that I have in my corridor that is serving me this, okay? And it's giving me, but inside of that router, there's the same thing as I have in my computer. There's a chip that is able to serve an HTML content, okay? And in this case, if I was within the router, so if I was controlling the router from within the router, and I put localhost in here, then I will be able to see the same website because I am within the router. But since I'm outside, I have to, let's say, say, okay, from within I am in localhost, but from outside of another computer, I can go here to this way and say, okay, which is the local IP that I have in this local network, and how can I visit what is delivering in whichever port. So that's what we are doing, but inside the Raspberry Pi. So the application CNC.js is serving.
Sorry, to go back a little bit. I mean, like, I understand kind of like the proxy is a server, I guess. Also, like, for you to access and send that information, you are using this proxy server, right? But my question is that, is Node-RED the one that connects the servers? Or where?
So Node-RED is an application, or application is like is a way of that Mac and Steve Jobs called scripts, but yeah, let's say it's an application that runs in the computer, and then it serves content in a host, in a port and with an IP. And any application can potentially do that. So in this case, CNC.js or Node-RED are the same thing. Okay, so we could have in here Node-RED as well, but in this case we could have instead of port 8000, port 9000, and we could access it, and we can tell the end. Well, to get it, so we could tell also the proxy to also serve the Node-RED content to the outer world through this door, the 443 door, to the outer world, and have both of them accessible.
Okay.
In the same way. How would we do that? For example, imagine that now we go here. When we go here, we access the CNC.js application, but imagine that I had created another, what we call location in the server that was Node-RED. And whenever I visit that, the server will give me Node-RED instead of the CNC.js application. And I could have done something like hello, doc.txt, and well, there's nothing in there, but if I put a file that was hello.txt in that address in the Raspberry Pi, then it could also be served. And that way I serve static content and applications at the same time. Okay?
Okay, okay.
That is all very well documented in, let me find my notes.
Óscar, what is, while you find them, what is Hopto? Hopto, it's like the platform where you do the dashboard, or?
No, Hopto is just, okay, so because this is like something with that we don't want to spend money on. It's a way to manage the DNS, so the domain name system that basically will tell when you write cncbythesea.hop2.org, will tell will redirect you to the IP address that we have in IAC. But it's basically this website that is called NoIP that has a bunch of free DNS services that you just have to renew every once in a while, like every month, and that way you can just have a temporary domain for a service, for example. So basically, when I go in here, let me actually show you.
So in that way, you don't have to buy a domain name.
Exactly. The only thing that they ask is that you have to, wait a second. Okay. What do you mean? Login.
Guys, just a second to tell, I'm going to use the CNC if you don't mind.
Of course. One second. So here, basically you can have host names, and we have the cncbythesea.hop2.org. You can choose these ones, but it's basically what they give you, some different options, and you can map them to an IP or URL. This is my the one that we used last time, and this is the one that we use for this session. And this is one of the static IPs that IAC has. Okay. And basically this service just allows you to have DNS records that will allow you to, when you go here, redirect you to here. The only thing is that if you don't pay, you have to renew them every month.
Oscar, and why don't you have the camera with the CNC by the bay.hop2?
You could actually, if you go here.
Port 8080, it works.
Yeah, the only thing is you have to request action string. So it's the same. Actually,
Wow.
anytime that you write this, it will be somehow replaced by the DNS servers, or somehow replaced, not by the DNS servers, but you get my point, and redirected to that IP address. So it's the same.
Oscar.
And yeah.
So you should be able to do the same with a GitLab page or GitHub page? No, because you don't have the static ID, no? IP for this.
Exactly. I don't have that. But the way that you do that in for example, imagine that we want to publish this in a GitLab page. The way you do that is that you put a file in here called CName.
Hola, hola. Perdón, chicos.
So imagine that we wanted to deploy this. The way that you would do it is that you put CName in here. So you create a new file and you call it just CName, C as in casa. And inside that file, you just put the domain that you want it to be redirected to. And some pages, well, some services like GitLab or GitHub allow that redirection already. So they integrate that within their services. So that when you build a page with in GitLab pages or GitHub pages, if you have that CName, they will redirect that there. But of course, you need to have the domain separate. So you need to have it provided by your company or whomever else. Okay. Or instead of doing this, you could just have your own hosting in Cloudflare or DigitalOcean or Amazon Web Server or things like that they just do the same thing as we did with the Raspberry Pi, but in the cloud, well, in their servers, which is not the cloud, it's just a machine somewhere else in the United States or whatever, that host all these pages for a lot of people. Okay.
That has to be, sorry, cname.md?
Sorry?
cname.md in GitLab?
No, it's just CName.
But it doesn't have
I put it in the chat.
Okay. And another question, if I already have like a domain name, I could host it in my Raspberry Pi and not buying hosting space to anyone?
Yeah, you could do that.
Okay, thank you.
The thing, well, here I put the instructions here because we have to talk a little bit about certificates and these things. So this will make sense a little bit in a little. So what is the diagram? Here. So here we have the application that is running in the local host that is serving data in the local host, the Raspberry Pi is serving data in the port 8000. Then this NGINX server is doing the connection between this application in the port 8000 and redirecting it to the port 443. For 443, you need to put, for HTTPS, you need to put what we call an SSL certificate, which is like the way that we tell the internet that our encryption is secure. There are SSL certificate providers, but there are some of them that are free. For example, let's encrypt is the one that I used, is supported by Mozilla and this Electronic Frontier Foundation and and many other people. But basically you generate your own certificate with a small script in the Raspberry Pi that talks to these people. They give you a certificate and then they deploy it and tell everyone that, okay, this connection using this certificate is secure. Okay, and it's generated by Let's Encrypt or the Electronic Frontier Foundation. We could serve this in port 80, yes. The only thing is that we didn't want to do that because this login here then would be sent in a non-encrypted connection. And then probably a lot of people could end up accessing into the machine and controlling it from their very remotely while we are doing it, because they probably could have stolen your password or these other things. Okay. Now, how do we access the internet in IAC? IAC has the same way, the same routers as we have at home, but they also have what we call an static IP. Static IPs are IPs that IAC bought at some moment when they installed the servers and are available for us to use. And one of them is the IP that we used in here, the 91, this one. This IP is an static IP that IAC has. If you go to number, I think it was 8, or number 7. So you see number 7 is IAC Cloud, a backup. Number 13 has nothing. Number 11, I think has something else, but basically these are servers that IAC has and that have public IPs. One of them probably is the website, one of them probably is the IAC Cloud, etc. I think Guillem or someone else set this up a long time ago, but basically we have some ports available in which we can access, and we don't need to do what we call the port forwarding technique before. These IPs have to be assigned to a machine inside, because the router itself does nothing with that IP. The router has its own IP, and we have some extra ones. So those available ones, we can assign it to different machines inside, but only one at a time, of course. So the Raspberry Pi has at this moment a static IP. And that static IP, we have to specify it in the Raspberry Pi so that it knows that, so it publishes to the router, it tells the router, okay, this is where I am, this is my name now, I am not 192.168 whatever, I am this static IP, I want it for me. And then any connection that comes requesting that will go to the Raspberry Pi, and when you access in the port 443, which is when you type HTTPS, it will go into the application, and then from the application you can control these things. The cameras are also connected via USB, and yet another script is releasing, opening them with the IP, but in a different port. So the port in this case is this one, is port 8080.
And can we open as many ports as we want, or there is a limit?
You have 65,000 ports, I think.
Thanks.
Of course, someone has to manage all those, the stream of data. So if you open 65 video streams, 65,000 video streams, you will fuck it up. And of course, some of them are also restricted. And you can see that.
How to burn a Raspberry Pi in 0.5 seconds.
So if you go here, this is a list of the ports that are used by certain services inside machines. So for example, when you use SSH is number 22. When you use Telnet is 23. 80 is HTTP. 443 is HTTPS. What was MQTT? I think it was 90. MQTT is 1883, etc., etc. Okay, and all of this, you see that the list is very long, but you have, well, a lot of them. I think, for example, yeah, the game engine, Steam, they use these ones. But it doesn't mean that you can use them. If you don't have Steam installed, you can use those ports because they are not using them. But if you had it, you know that these are going to be reserved for the Steam game engine. Okay, some databases, etc., etc. Okay.
But that means we can only have one port per function.
Yeah, this was what I wanted to ask.
Exactly. Yeah. Okay. So the communications can only go through one door for each specific application. Exactly.
So let's say we cannot have two HTML pages. We can only have one.
Yeah, no, HTML. No, you can have as many as you want. The only thing is that how are you gonna serve them is so that the door is somehow just the channel in which you serve them, but you can have as many, let's say, files as you want. And for this, let me go back here. Where is this? Networking. Serving static content. So websites, normally like the ones that we have for documentation or even this website, is static content. It doesn't change. It doesn't do anything. There's no application in the background. So you could have as many locations as you want. And for example, this is your server. This is where, this is the folder where you have it in your computer. In this case, it's a folder called www/data. In the root folder, you can have one website. In the images folder, you can have another one. In the MP3 folder, you can have another thing, etc., etc. Okay. Of course, this is a little bit more complex, and even you can have both static content and an application. And in here, for example, what we did, and actually I will show you the file, you can have, if you go here and you want to replicate this, you have the example files of the Raspberry Pi, of course, with usernames and everything masked. But if you go in here, the NGINX proxy server, here we say, this is the server. We are listening in 443. This is where the certificates are. This is generic stuff. This is the server name. And when you go to the CNC by the c.hop2.org, the normal location, you do the pass to this guy, which is the CNC.js running in port 8000. So I need to have CNC.js running in the Raspberry Pi so that you can access it. And that's it. There's nothing else. This then NGINX is running the server using this configuration file. And whenever something comes in 443, it's going to use these certificates to verify the connection and use this and show whatever is in here in this localhost. The other ones, the cameras, are not specified in here because we actually don't need them to secure them or anything, just for the stream. But we could also put them in here, and whenever you visit camera 1, then you put the camera stream 1, and whenever you visit camera 2, you have the camera stream 2. We could secure that connection as well. Then, do you have any questions? I know this is not like it's a lot of content. I'm mixing a lot of things.
Was it easy, kind of easy to configure, or not especially?
Yeah, I mean, the thing is that given the situation now with this type of tools, NGINX, and especially the one that CNC.js that we found, it was easy to configure. So right now, if you want to do this type of things, you can, more or less, if you know what you're doing, you can do it in less than a day to run your own application. And actually, we did a sprint on Tuesday, and on Tuesday morning, we discovered CNC.js, and in Tuesday evening, we were already streaming and testing things from home. So it is possible. It's not that difficult, but you have to understand some concepts. And of course, as I like what Guillem says when he explains the basics, is like understanding the foundations or the basics allows you to be creative. I think this is particularly true in this type of thing, because right now, when you see this diagram, after all the classes that we've been doing, this shouldn't be so complicated that you don't know what you're seeing. So in here you have a machine, you know what USB is and how these things are connected physically. You know, or you will know how the Arduino talks to the Raspberry Pi, what G-code is, the Raspberry Pi, the different applications that it has inside, and what is an IP and what is a port, etc., and how these connections are done. So even if this could have some weird words like NGINX reverse proxy server, it should be understandable, because right now at this moment of the course we have touched all those things.
What's reverse in the NGINX reverse proxy server?
Sorry?
Why? What's the reverse in the reverse proxy server?
Because it's taking, I think, I don't know specifically, but I think it's just because it's taking this content inside, but that is within the machine and serving it.
Okay.
I'll say, but I don't. I don't know exactly. There's nice documentation here. So if you want to replicate this, and I think that the powerful thing is here is not that we are just able to do it, but that you with this documentation could also do it, is that in here is everything is explained and how to replicate it. There's quite a lot of stuff, and some of these things are meant to be complex, so to be complex somehow, so that you see how to make things reliable, but it should be somehow accessible. One of the things, for example, is that what happens if the Raspberry Pi turns off and it turns on again? Is the server still running? Will it crash, and then do I have to be all the time trying to do it? Try to launch it again, and if it falls at 5 a.m. Or it collapses at 5 a.m. and reboots, it will be off for 3 days until I see it. In principle, that shouldn't be. So you should be able to start services in the Raspberry Pi, or in general in any machine, with what we call services and system control. In the Raspberry Pi is called services, and if you want to read a little bit about them, I'll share with you this, where is it? This link. That basically is a way for the Raspberry Pi to launch all the services that are available. For example, a Linux system, sorry. A Raspberry Pi is a Linux system, so any Linux computer will launch using this system called systemd. Basically, we specify what scripts and with which options we will launch when we boot, or whenever things are available in the machine. And this is what we did. Yesterday, Edu told me that the Pi was, there was a bad gateway, so there was nothing being given in the Raspberry Pi. And it's because I closed the connection, and then by that I closed everything without realizing, because I hadn't set this up. So imagine that we want to start the streams automatically. We could make a little script that is called run camera streams or whatever, that only has 2 lines. One line is to launch camera 1, the other one is to launch camera 2. This is just something that you would put in your command line. We can then create a service. So this is one script, and then we will create a service that runs that script every time that we boot the Raspberry Pi. And for that, you just create a text file that specifies how to do it and when to do it. When to do it? After the networks are available. What to do? Using this user, whatever, run this script. And then every time that we boot the Raspberry Pi, this script, the run MJP and JPEG streams will be run, and then the cameras are available. The same for the CNC JS script.
So the file, it's the run mjpeg streams.sh.
So this is a script that contains this, which is basically starting the cameras and sending them to the port 8080 and the port 8081.
But you were saying something that you need to create a document in the...
Exactly. This is the document. It's here.
And what kind of document is it?
It's called mjpeg-streams.service. And you put it in this library, in this folder, sorry.
Okay, so it calls it each time it reboots.
Exactly.
Okay.
So for example, when you install Node-RED, you could install Node-RED and the service. And whenever you boot the Raspberry Pi, the service will start by itself, and you don't have to do it manually. And you don't have to worry. And every time that you connect, the service will be running. So you can, if you follow these instructions here, then you will be able to do it also yourself. And here explains a little bit how to make all the certificates, install nginx, and make the connection, run it, etc. So that at the end you arrive to doing the control remotely. And I put, Pablo, your mandala here in the docs. Hope you don't mind.
Nice.
So I think for those that are willing to use these type of things, you shouldn't be afraid because it's very feasible and now and it's documented. So for those that are willing to run a little platform or that want to make a little service in a Raspberry Pi, don't be scared because you can do it. And also we can give you support to do not only the things with the physicality of them, but also to deploy them and make them at least temporarily accessible so that you can also experiment with these things. And the end result, you see it, that is running and will be running for some days at least until we get tired or go or move on to something else. But yeah.
Is there a recommended OS for the Raspberry Pi to run a server? Like, I don't know, Raspbian or?
The system.
Yeah.
The OS, just use Raspbian. Yeah.
Raspbian, okay.
Yeah, I use the version. There's the last one is called Raspbian Buster. So they use Toy Story names to name the versions of the OS. So the last one is Buster, but I use the one called Stretch. But and Stretch is the last one before the Raspberry Pi 4 was launched. And I use a Raspberry Pi 3 with a Stretch. But in principle, all these things should be available already in the Raspberry Pi 4 and Buster as well.
But if I do sudo apt get update, sudo apt upgrade, it would get like to the latest version too? Or it will stay in
of
the
of that so apt, so apt, sorry, is for the let's say the scripts that you have in that version of the OS. It won't update the OS.
Oh, okay.
It will just update the different commands or scripts that you have in the Pi. For example, I don't know, Node-RED, it will update, well, Node-RED specifically no, because Node-RED is in NPM, is the Node package manager. But other things like, for example, libraries and this type of things, it will. But only for that specific version of the OS.
So talking in Mac language, it would be like, it would stay in Catalina or in Sierra, but it will update the libraries in Sierra or in Catalina, not changing the...
Correct, exactly, okay. Exactly, yeah. And this is it. Here you have also some other things. For example, how to tell the Raspberry Pi to have a static IP address is in here in this interfaces document. And here, basically, ETH0 is the Ethernet cable of the Raspberry Pi. We want a static, and this is the static IP address, the network mask. So it's normally like 255, 255, whatever, but this is given to you. So it's just like when you were in school and you were doing a math problem and they told you, you have 5 apples and you have 6 people. So this is things that you know already, so you don't have to worry about these things. And this is the router IP. Okay. And basically you put this document in, so this file, it already exists, of course, you just have to modify it. You put it in the folder that is interfaces here. ETC network interfaces. So this folder, you edit that file, and then you have an IP address. Okay, and also there are like a lot of links that I put in here. For example, this one for setting the IP address. this website, this guy is a very amazing developer here in Catalonia. Is from the Thin, I think it's from the Thin network. He has very good guides on how to set these things up, and explains a lot of things with the network, how to set up Node-RED, for example, how to send Nginx, what is SSL certificate, why to do it, how to do it, etc., etc. And actually, you will see that a lot of things I took them from this guy as well.
Can you share us that, please?
It is in the documentation. It's in here. It's a Tinkersman site.
Gracias.
So imagine that, I don't know. I don't know if Daphne is here, but the other day we were talking. Imagine that you would make your final project auto-generated, like a text file that is auto-generated, talking about I don't know, the stupidity of making a final project or something like that, but it's auto-generated by a machine. So you could have a Raspberry Pi that runs a script that generates that document and serves it online, and whenever someone goes in it, it receives a new final project, a fake final project, and the whole thing, the whole metaphoric idea is a final project in itself that gives you weird final project. And you could build that in a Raspberry Pi that runs a script and then serves you that content using this type of things. Or you could do, I don't know, a control system or a reporting system for your plants, or a way to control Edu's machine, the 6-pack CNC, or a production manager for these machines, or an interface that deploys the temperature maps that Zoe is building, or an website that shows the beats, let's say.
Óscar, I think actually the 6-pack milling machine, I already went through the code. And as the Arduino deploys automatically a web page through an IP, what you just need to do is a forward forwarding to your router, so you'll be able to access directly remotely.
Yeah, so something like that. But I'm saying that you could also start using these things so that you can bring them to like another level, exposing them to the internet, or even if it's in the local network of IAC during the presentation, it doesn't matter. But you could start using these things. And with a 30 euros computer, you don't have to go to Google or DigitalOcean or something. It's 30 euros that Raspberry Pi costs.
5 euros, 50.
Exactly. For 30 euros, you have all this. So this is, I think, the beauty of all these open tools that now allow you to bring these things to like a next level. And this is it. I think, well, we went through a lot of information. Everything is documented in the project. So if you go to gitlab.com/FabLabVCM projects, you will see that not only this session of the CNC by the sea and all this is documented, but also the Edu documented the CNC machine, the Kraken.
Wow.
So it will be soon.
This machine was never meant to be documented.
Okay. Well, but for example, the 6-pack machine is I think it is, right?
Yeah, that one, yes.
So this machine has all the documentation. So the idea is that we try to build this type of things little by little, but you can replicate them and build them yourself as well, and try to even improve them, because of course there's a lot of room for improvement in everything.
Actually, Armand, yes, the ESP32 has enough space to host a full web page with the interface, the firmware control, because this machine, the 6-pack milling machine, is going to use Gerber as base code for freeware control that is lighter, much lighter than actually Marlin. And it will have enough space to upload 1 or 2 G codes. So actually in the PCB that Óscar has designed, we have included a SD card reader. So you can upload the codes directly through the ESP, but to save them as external flash memory. And the Kraken, definitely actually, I just took me 1 year to build it in like spare time. And it's a mix of, for example, the left side motor is different from the right side. It's just basically it's a super Frankenstein. And we just start enabling things like 1 week I have 5-10 minutes. Okay, I will enable all the servos. 1 week, okay, I will upload the firmware. So I don't even know exactly what is inside. I have saved the full firmware, is the thing, and I have the fabrication files from 0.1 version to 2.5. But I can explain you short term how this machine was built. And one of the things that made me not document it is because we was not meant to be reproduced, but to be hacked by you. So it was no point of documenting something that was supposed to be hacked. I can share the screen a little bit. Okay, let's go into the browser. So, hello, this is a Prusa. Just a little bit of the machine design. This is about more next week version, but as the next week is machine design and machine builder design, and we want you to focus on the 6-5 milli machine. We want to introduce a little bit of what is mechatronics. Maybe we can go super fast along the session, Óscar?
Sure. Yeah.
Could we do a mini bio break?
Yeah, I was gonna ask.
Okay.
No.
Thank you.
No.
Okay.
What are you talking about? But you're not machine, so what?
Okay, let's do a bio break. I stopped the
Thanks, see you.
recording.
See you.
Okay. So, mechanics!
Yay.
Okay.
I think I could like spend 5 hours watching that GIF.
So we will go into this quite fast because today is not only a mechanics, it's a little bit on how, for example, the Kraken was designed and everything. So the first thing we want to understand is actually we want to control machines. That implies motor control, electronics controlling motors, system of movement, etc. So most of the machines, there are different kinds of the machines, but they are englobed into what is called moving in axis. Let's say the standard one and the most easy to understand is a Cartesian system. You have a platform. Sometimes the platform doesn't move, but in this case the platform moves. It will be the x-axis. You have the second carriage, that is the y-axis. That is what we call the bridge in most of the machines. And we have a third system that is the Y bridge that moves up and down, or in cases like the Kraken, the Z moves by itself down. Guys, who put the the servo down, plunging into the sand again? Each time I look at the camera, somebody screwed it up. Okay. So we need to understand that when we want to move things, we need to define first how fast we want to move, what kind of loads we want to move, because obviously it's not the same moving a big motor like the CNC router motor, or than move a small laser that doesn't have almost inertia because it doesn't have weight. We are only basically moving a small mirror. So we need to understand degrees of freedom. That is how much we want to move. Traditionally, you have a rotating axe, and if you only have two rotating axes, but they are locked, this is a steady system. That means this system cannot move. For example, if we have this one, we can move the system and produce an arm movement. Onto the machines, how we translate movements. Actually, the most standard is to use what is called rails. Is a part that slides the same as you ice skate on ice through another system. Usually the rails has to be really sturdy. So actually they only produce movement in one direction, that is a sliding direction, because you don't want that this moves also in X, Y, or Z three-dimensionally. You want to move only along the axis direction.
One question. In the diagram before, is there a difference between the circles and the squares? Up. Yeah. In that, no. Yes.
Yes. This is more or less a standard terminology on how you put axes. Let's say this is a rotational joint. It means it cannot slide in X, neither on the normal, but can rotate. Allows rotation, but not sliding.
Okay.
This allows movement in all the directions and rotation, but locks rotation in the normal of the string. This one is a sliding joint. It means allow only slide in X, not in the normal, and also allows rotation. Let's say it's the same as when you brush something on the floor or wipe with a cleaner.
Yeah, so if I would have the second one, the B1, but with a square, I could move it because
exactly.
one would slide. Okay, thank you.
Exactly. Usually what we use for most of the machine is linear systems. It means systems that only allows rotation in one axis. Rotation, more than rotation, is sliding in one rotation. So actually we don't use rotational axis, what we use is sliding mechanism. There are a lot of types of sliding mechanisms and ways of translating rotation into linear movements. For example, the simplest one is something that you use every day, but you don't see because it's inside your car. Your motor, actually, we want to create explosion. The explosion makes force and pushes the piston, and that connected to a rotational axe, we can transform it into rotational movement. So we can translate linear to rotational, but we can do the opposite. For example, a compressor, the motor that produces the energy is making rotation, and we translate it to a linear system that compresses air and releases air all the time. So depends on where is your source of energy. In this case, you are producing rotation or you are producing linear motion. We have something that there are gears. Gears, something that you have seen a lot everywhere, like from small toys, whatever, is to allow translation of where is the rotational movement. For example, if the motor is here, but somehow we want to activate something here, and you cannot put the motor in this direction, you can use gears to translate rotational movement to another position. This is done widely into gearboxes, and if you change the size of the gears, you can increase torque. The most clear example of this is your bicycle. If you want to go faster, you can either move your legs faster, but there is a moment that you cannot move them faster, but you want to increase the amount of movement translated to the wheel. You want to increase the ratio of gear relationship. So, for example, if you have a big wheel that has connected the motor and you translate it to a small wheel, you are, by just, let's say, 5 degrees movement of this one, you are making 100 degrees of movement of this one. So actually you are producing more rotational speed on this one, but with less torque. So if you increase your speed, you reduce the torque. And if you do the opposite, if you have a small gear that is the driving system and you connect to a big gear, what you do is you reduce the speed of the big gear, but you increase the torque. This is something that happens a lot. For example, when you have a really small motor, but it needs to move a really heavy load at low speed. We use a small gear connected to a larger gear. There are different types of gears. That depends on the design. The standard one is a straight one, but we have helical one that the teeth of gear is tilted. This is widely used to reduce noise and smoothness on the contact. Why? Because when one gear connects to the next one, is a hit, a direct hit, one spoon, let's say, to the other spoon. It's not smooth. Meanwhile, if you have an helical, you have a gradual touch between gears. You start touching here and you finish touching on the whole gear when you have a little bit of more movement. So helical systems, helical gears are used to make less noisy gears and also smoother gears. Something that, for example, you might not know is you have noticed when you drive your car in first, second, third, fourth, or fifth gear, the motor sounds different than when you push the reverse gear, no? Like the reverse gear of a car sounds really different. Like it's completely different sound. Why? To make the cars more smoother on driving and reduce the noise, the first, second, third, and fourth and fifth gear of the cars are helical. And you are never driving, or most of the time you are never driving in reverse. You just do it for 5 minutes. So the straight one is used for the reverse one. Why they use different kind of gears? First, fabrication. Producing an helical gear is more expensive. Second is torque translation. Helical gears translate torque less efficiently than a straight gear because they have more friction between the teeth. Basically, you are increasing the amount of touching surface. So that reduces a little bit the torque. I don't know if you have gone to a rally, but rally cars or like race cars, like professional race cars, actually the sound of gearbox is really similar to the reverse of a normal car. Why? Because all the teeth on a race car is straight because they want to take the most amount of power from the motor without any power loss because of friction. We have straight bed level gears. For example, we have yes?
Yeah, sorry. And so why don't we do that for the regular car if it's cheaper and more effective?
Noise and comfortness.
Okay.
Actually, you have noticed that, for example, when you accelerate in reverse, it's really easy to make boom, a super fast movement, no? It's not that smooth. That's because of the straight translation between gears. They actually impact ones against each other. Also, as they have more impact and they're translating more force, if you want to make them last longer, you will need to reinforce them. That also will make the system more expensive. Actually, the racing gearboxes are not meant to last a lot. They change it each more or less 2 or 3 races because they get wasted. Because they want to use less material, they don't want to make them last longer, but they want to have the highest power transmission. And they don't care about the noise because the cars are already making a lot of noise.
Here, these are not gearboxes, gears, but I have them at home, some of them. This is from, I think this is the distribution of an engine. And this is what happens when you have metal particles in the oil. So these things have to be lubricated, of course. And when you have little particles of metal inside, because something is wearing or something, then you break the teeth of the gear. But this, for example, I can bring them one day to the lab so that you can see them. This goes inside an engine in like a normal Audi or something like that, I think.
Oscar, do you sell spare parts of cars, it seems?
Yeah, I have a website actually. Look.
Really?
No, but really?
Yeah, look, right.
Yeah, because you always have like parts of cars.
You never stop surprising me.
Look, it's called, here, I put it in there. It's called Óscar.
What?
Yeah, it's a massive website. No way.
No, I'm not kidding. I'm kidding. This is a famous one that just happens to have the someone a name related to me.
You wouldn't be the tabla without this.
But in France, this is very famous website
Oh
for parts. Óscar.
Funny.
Óscar.
Nice.
That's funny. Actually, maybe we can see here the straight one.
I like that one, Benjamin.
We don't see. It's not here. Fifth, fourth, reverse. No, it's not here. We don't see it well. Okay. So, for example, we have straight bed level gears. What happens if you want to translate one directional rotation to a 90 degrees? You use like slice it at 45 degrees gears. This is something that is also in every car because ¿cómo busco esto? Diferencial, ¿no? Diferencial, coche. For example, on the cars, usually the motor is on the front and you are driving the back wheels. And you do it by the torsion bar, rotational bar that is connected from the motor to the back. And you have this little box. This is a differential. It's a much more complex system than this one, but it's based on the same concept. So how to translate rotational movement in this direction into the wheels one? Actually, differential, if you look at it, open, it looks like this. Actually, it's this. We have duplicated system because the wheels rotate at different speed. Actually, there's a lot of videos. There is a really, really nice video on differential of cars. And it's from Chrysler in the 60s. And it's one of the best videos I ever seen on YouTube. I think it's Chrysler, no? Yeah, this one. Actually, it's from the 37. Oh my God.
Chevrolet.
Okay, let's see. Yeah. But they explain what is a differential, but here they do it with gears. These are all bed level gears, like at 45 degrees. Sometimes they are low at different angles, but the standard is to be at 45 degrees. I recommend you to watch this video. It's really, really, really educating. We have Helix one. Actually, is the same, but mixed with helical, so it's even smoother. We have pinion rack, that is a straightforward translation from a rotational move to a linear one. Do you recognize this kind of system? You have it in the lab. You have seen it.
Stepper motor? No.
The CNC
machines.
The milling machines, they use this system because they want to have a straight translation from the movement without any jerk. So they transform the rotational directly to the linear one with the gears. The good point is gears, they don't have something that is called, they have less amount of backlash and less amount of jitter. So backlash, I can only explain, it's really difficult to explain this without making a physical movement. You have the teeth of the gear and you have the big one. If you are moving into one direction, you are pushing all the time on the left. If the teeth is not completely new, like this, it will have a little bit of space. So you are pushing in this direction. What happens when you reverse? You are pushing now this movement, no, in the other one. What happened? I have made a movement, but I have not touched this one. So I'm not translating all the rotational movement into a linear one. This is called backlash. And actually, it's the worst thing that can happen to a machine. The known direct translation of one rotational or linear movement to another system. And actually, this is what gives accuracy. Accuracy of the machines, one of the biggest constraints to determining the accuracy of a machine is the amount of backlash, because all the machines have backlash. If they don't have backlash, at really small scale, you will not be able to move the teeth away because it will be a straight direct connection. The smaller it is, more accuracy, but more difficult to make the movement and to take the teeth out of the system. We have planetary gears to making reduction from a small gear to a linear one while keeping the same rotational axis. This is widely used in gearboxes and rotational motor systems. Like Mazda has a lot. We have the belt and chain. Why we use these systems? These systems are used to make a rotational translation on long distances. Because let's say you want to move a wheel that is 100 meters away, you don't want a gear that is 100 meters in diameter, or at least 50. If they are both the same dimension, you need 50. So actually you use chains and belts. The difference between both is the teeth. Belts usually don't have teeth, and they are done with kind of rubber reinforced bands. Compared to chains, they are full metal in general. They have, of course, some silicone and rubber O-rings between the systems, and actually the chain is what you use in the bicycles and motorbikes and high-power drain brake systems. Why? Any clue? That's because the chains, even if they have a lot of friction between all the different parts of the mechanism, they have a better translation in the torque, because the belt or the chain, in this case the metal chain, doesn't elongate. When you take a piece of cord or rope, you can straighten it a little bit, and it changes the dimension, no? With a chain, that effect is reduced a lot. So actually, by that, you also reduce backlash. You have a more straightforward translation from one wheel to another one, and they are compensate at the same time. So chains, in general, they are better, they are stronger, they last longer. But what happens if they have high maintenance? You need to lubricate them, you need to change them, because they have a lot of friction and they get wasted. For example, you have seen that clearly with your bicycles. If you have used for 1 year the bicycle, you need to put oil. If it has like 5 years old, you need to change the chain because it gets wasted. Because there's a lot of friction between all the different cylinders of the chain. Belts, on the other hand, are really smooth because they have low amount of friction, and they translate, and the movement, they don't have friction on themselves. It's actually, we are working with the materiality. The material bends and accommodates to the shape. So that makes a really noiseless system, smooth, but we have problems. What? You see this, actually the rubber band also elongates. Of course, belts, in general, they are not meant to use with high torque systems. But even so, the belts are not just rubber. They have steel wires inside, and you also will need to replace them. For example, you have seen some Harley Davidsons, they use, and especially BWM, they want to make like driving experience of motorbike much smoother. So actually they use belts to drive the back wheel, to actually make not only, to make only come out of the motorbike the motor sound, not the chain sound. You have seen some motorbikes on the street, actually you hear more the chain than the motor. To enhance like the driving experience, they use belts to reduce the chain noise, to make it more powerful, the motor noise. This is also, for example, in cars, is used to drive the vents or the fans that cool down the motor. You don't want to move a high torque system. A fan doesn't need so much torque, so we can run them really nicely with a belt. For example, belts are also used in scooters. Scooters makes less noise. One of the reasons is because they use belts. And they have a continuous variable change transmission that is a CVT. I will not go really deep in this. We have cams, how to translate, for example, rotation into repetitive movements. Pistons, of course, and you might recognize this, for example, from the oil pumps for petroleum. This is basically this in really big. How to keep things in place, bearings. Actually, how to translate those movements or how to make everything round smooth. This is, for example, a linear bearing. This is a cylinder. The outer shape is this. When you have a cylinder bar that is made of steel and you don't have straightforward friction, what you do is have a lot of balls that they can move freely. How to say, linear bearing balls animation. Yes, here. So actually, the balls have a circuit. And this is the bar that you want to slide. So when you want to slide to the left, the balls need to rotate in this direction, clockwise. So what you do is the balls are moving like a chain. It's like a really small chain made out of metal balls. This could be done. This is a square linear motion guide, but you also find them in cylindrical ones, like these ones. They have the same systems. Sometimes they are elliptical, sometimes they are straightforward, etc. But in general, they all become like this. It's a linear slider. We have also ball bearings, that is to accommodate a rotational movement along a holding element. This is commonly used in shanks and any rotational axis. You need to constrain that the bar doesn't move in all the directions, only it rotates. So this has a lot of balls that allows the internal ring to rotate independently from the outer one. So the outer one is usually fixed and the internal one is the one that rotates. Bearings, they sell them in a lot of different options. For example, this is an open bearing. It means we can see the balls, and by so it's easier to fabricate. What happened? It's easy to oil and to have maintenance of these bearings, but this is not meant for dirty environments. If you put these ones on a skateboard, for example, in the moment you spend 1 hour driving down the street, dust will get inside and it will jam the balls. So there are options for these bearings. They are called seal bearings. Seal bearing. That they have kind of rubber protector. Depends on the level and how good what is made. They have protection rubbers so the dirt, oil, dust, water doesn't come inside. And this defines more or less the pricing of your bearing. We have cylindrical flat bearings. It's really similar, but instead of having balls, they have cylinders. These ones, in general, they are better for rotational movement, but they cannot afford any movement in this direction. If you move the bar in this direction, you will have a lot of friction and you will break them. So they are more sensible and they have more resistance, but in general, they last much longer. And for pure rotational movements, they are better. We have conical ones, special ones, and we have rings, etc. So this is about cantilevers. So, for example, you have seen the Kraken. Kraken doesn't use any of this. Actually, in machine building, Since, let me close Windows a little bit. For example, this machine, a Prusa, has a frame. The frame holds what? The sliding mechanism is the metal bar. To be able to move along the metal bar, we have some bearings inside here. So actually, just to make a linear movement, we need a frame, a sliding mechanism, a bearing, and a lead screw that is a kind of metal bar that is like this, that transforms rotational movement through a kind of nut to be able to push it farther or closer. Just to have a simple linear move, we have a lot of hardware. Luckily, and this is something that comes, let's say, from the maker world. For example, this is also the close-up of the linear system. Here you can see the bearing.
What's the point of having a lead screw and a cylinder to go along it?
Sorry?
What's the point of having the lead screw to decide, you know, the amount of movement, and also have a bar to go along them? Can't we just use the lead screw and the bar as the thing?
Okay, this lead screw needs to be able to rotate. If you want to slide, let's say, put the bearing inside the lead screw, the balls that are inside, they don't have a smooth surface to contact. They will have jumps because of the lead screw design. So you want to slide in a smooth surface. Do I answer your question, Benji?
Yeah, just.
So I think because if you put the weight on the lead screw, it's gonna bend a bit, and it's not gonna be a smooth movement, and it's gonna crack the.
Not really. Actually, the bar, the lead screw bar, is as strong usually as the driving linear system. What happened is you cannot just put this one. Let's say, for example, if I only have one bar, Benjamin, and I rotate to move it up, this one needs to be constrained in this direction, no?
Yeah.
If it's not constrained by another secondary bar, in the moment I rotate, it will rotate with me.
But there's two lead screws.
If you have two, that compensates. Okay, you can move up and down, but usually the lead screw, you want to have a little bit of flexibility to accommodate all the movements of the machine. They have to be kind of slightly free. Why? Because in the moment you put a motor to another bar, they are not designed by itself. There is a little bit of misalignment, and you need something that holds together, that accommodates that misalignment. If you have something that is slightly flexible, your whole machine is flexible. You want to avoid that.
Cool.
So there are some guys were smart. I don't know if they were these guys, the open builds, but they start thinking, okay, how I can reduce the overall cost of a machine. Where is the, sorry, too many things open right now. This lot. So how I can reduce the amount of hardware I need to build machines. So this is a standard aluminum 2020 profile. It's a something kind of standard in the industry. And they say, okay, if my frame is this bar, because usually what you do for building stuff in the industry, in different sizes, different dimensions, they have 2020, 4040, 5050, like the size of the square. The length is about the extrusion. Why I cannot use this to actually be used as my sliding mechanism? This, let's say, is good enough to slide, as is accurate enough. How I can reduce the amount of hardware needed, because I don't want to have a frame, a linear system, and a driving system just to make a linear movement. I have three systems that makes everything so expensive. So these guys were smart enough to produce a system that you can just put wheels to rotate as a, let's say, a big ball system to rotate along your V-slot. And at the same time, you have a really sturdy profile that is working as a frame, and we have a sliding mechanism. Of course, here we have some bearings, but we are reducing the amount of total bearings. Okay, we can have a frame and at the same time slide. That's good. How we transform the motion from rotational to linear one? For example, this is a full linear system. Now we need to be able to move this one. What is the cheapest driving mechanism that exists? One of the cheapest ones, belts. Gears are expensive. You need a lot of gears. It's metal, usually. It's expensive to manufacture. Chains are good. They are cheaper. We can translate long motions, but they have high maintenance, high noise. It's also like usually heavy system. We have, the slot belt system. Let's see if we can find something. Yeah, kind of, here, this one, more or less. The link in new tab. So they say, okay, I have the frame, I have the wheels, and I have a motor. What happens if I put a belt that is coming through the rail, push it through here, to a rotation, and move it through here? In the moment I rotate my wheel, I'm gonna grab the belt and release it through here. Let's see in here, I think this is a video. Maybe, maybe not. So basically you are taking the belt, moving through here, and releasing it in this direction. So if you rotate the wheel counterclockwise, you are actually grabbing belt, and by so you are moving the carriage. So these guys, actually, this has become quite a standard, not in the professional world because it doesn't give super enough accuracy. There is a lot of problems of backlash, etc. But this reduces a lot of the amount of hardware that you need to drive any kind of system. And this can provide accuracy enough to 0.2 millimeters, more or less, like depends on how well you design the system, etc. Of course, it's not going to last a lot of time. You are using belts. But what is a lot of time? Really depends on your application. Like this can last years if you treat it nicely. Also in how thick is your belt that you design. So these guys developed a full ecosystem that is open builds. They have store, etc. And they build a community that basically they just output, let's say, lot of standard parts like profiles in different dimensions, wheels of different qualities, bearings, and some plates, metal plates and braces that they can assemble their system. Let's go maybe to here. Machine bundles, material, let's go. So for example, linear rails, this lot linear rail. So they sell different kind of profiles, depending on how sturdy you want to make your movement. Plates, this lot plate, to have different accommodation of the wheels, because maybe you want to make a small translation of rotation. So they have this plan of plate. So they have built a full ecosystem that allows linear translation movement to rotational in a blist. It's super easy, and it's quite cheap because they are using low quality components in a way. When I mean low quality, it's like not industrial graded quality to last 10 years in full 24 continuous use, but good enough. Actually, they have some wheels, for example, they have the extreme wheels. They are made of bell ring. Bell ring is a super expensive and really nice material that has really low friction. Actually, this wheel doesn't need to be replaced unless you run it like for 100,000 hours. So they have, let's say, the plastic ABS wheel or the Delrin one. So the full Kraken, we want to build a simple enough machine. We built using this system. And we started, and actually right now, most of the 3D printers they sell, the Chinese 3D printers, let's say call it standard, use this kind of system. And that's one of the main reasons why 3D printers have become so cheap right now. Not only on the hardware, on the software and firmware electronics, but also on the hardware, because they have reduced by half the amount of hardware that you need to produce a machine. So all these, for example, they are machines designed by the community. If I go to the Open Build store, and just to give you another look, Open Builds, I want to go to the Open Builds store.
Edu, I shared you the links for the FarmBot documentation. I think they have really nice images of what you're saying right now about how the cross sliders work and the hardware, and all the links are for buying it in Open Builds. I think the last one shows the cross slide. That one has more like videos of hardware extrusion and everything.
Okay, that's good. So actually right now there are a lot of companies that sell not industrial quality graded machines, but enthusiast machines that they provide really good quality at a really low system. For example, Xcard, that is one of the most famous like garage CNC, uses this system. And this has a super huge community. And actually they have a main frame with the belts and everything. So basically we took these kind of things and kind of reinforced it as much as we can while keeping the cost down. So for example, we use a 2040 profiles to make it a little bit stronger. We put, instead of having a flat base, we made a secondary double frame under it to level the set. And for example, it was really easy to assemble. The only part that we designed it, instead of buying the parts, we actually mill in acrylic all these side plates. And I can see shop, maybe Xcard, or let's go for Xcard CNC pictures. Yeah, for example, this one, this one, yeah, and this one. So actually what we did is design our custom plates. In this case, we use acrylic of 10 millimeters because it's strong enough. 5 is brittle, but 10 is quite enough, quite good resistance, doesn't flex too much. And we design a system like this on the machine. And that's how actually we drive all the X and Y carriage. Actually, you can see here, this is the acrylic plate, the wheels, and the belt moving through the wheel. And it's good because it's a quite clean system that allows linear translation of movement. It's a big machine, so actually this is heavy. So instead of using NEMA 70s, we use, for example, NEMA 23 to have a little bit of more torque. Nice drawing, by the way. So we designed it to make it as simple as possible. Instead of designing multiple parts, one plate for the Y motor, one plate for the Z, what we try to simplify a lot, that is have just one plate that holds at the same time X, Y, and Z carriage, and 2 side plates that are symmetrical. I don't know if you can see in the other image. Well, this here just, but we don't see. That is actually super simple and really similar to this one, but in acrylic. So that's how the hardware part was done on motion linear system translation. We can take an overview of actually control of this machine, how we control these things. Nice drawing, I like it. What is the electronics behind it? So one of the things that has made all the fabrication movement and everything is, of course, the Arduino. And you know, Arduino, quite simple. And basically, all the machines have a system like this. That you have several motors. Usually, there are stepper motors, because you want to move accurately, like have step control, know how much you are moving, what is your movement, and you have some stepper drivers, and you have them controlled to an Arduino. Of course, having everything like this will be a mess of wires. So there exist several solutions. For example, one of the most standard one is a CNC shield. That is a small prototyping board that just you connect on the top of an Arduino, and you have all the connectors ready to connect all the hardware that you need and your stepper drivers. Where are the stepper drivers? Actually, this is small connection for this kind of small stepper drivers. This is the simplest machine that you can build. Use an Arduino Uno with a stepper driver shield. That is what it basically is, this thing.
Does that shield also includes the relay? It has like a relay on the left? No.
Relay? No.
Yeah.
No, it doesn't have a relay. You will need to connect. Usually that's done in the spindle, like it's a digital output. All these ones are digital outputs, so you can connect whatever you want here, an LED, etc.
But how do you manage to the outer power supply, that 12 to 24 volts?
What do you mean?
No, I thought that you needed a relay to also use that. No.
This is just power.
Okay.
It's always connected. So when you design a machine, the first thing you need to do is know the size of your motor. And basically it's the main hardware of the machine to know the amount of torque that you need to move. For example, if you go to a stepper online, one of the biggest providers of stepper motors, you can choose by size of the motors. And for example, the standard for 3D printing is 17, the standard for CNC is 23 or 34. Let's go to a 23. And you can choose by torque. You know that your machine will need to push, for example, if you want a machine that cuts aluminum, the forces for cutting aluminum, if you explore a little bit, they will be at least 90 newtons per centimeter. You need 9 kilos of push per centimeter. So you will need to use a stepper motor like this. For example, I want to be a 1 degree control. So this stepper now gives me with a holding torque like this, give me a rated current of 2.8 amps. With that, I know that my stepper driver needs to be able to provide 2.8 amps of power consumption. These stepper drivers that are kind of the standard, they are nice, they are cute, they are really small. Actually, they are something like this. They look like a nail. Yeah, exactly. They are nice, but they are usually rated, for example, a maximum of 1 or 2 amps. I would say 1.5. So depends on your system. You might want to jump to something like this, that is exactly the same, but packaged with a big heatsink and a more powerful double H-bridge. That is what you need to control a stepper driver. So this and this is the same. The difference is the amount of power that they can supply. Actually, if we zoom in this, it's able to provide current 3.5 amperes at maximum. So actually, this driver is designed even to drive an EMA 34. So, okay, we know that we need to move the motors. We have more or less choose the motors. We have more or less know that the drivers are like this. And we cannot use the small ones. And we cannot connect them like this. There is no problem. We can use the pins to take cables out and connect directly, for example, to the Arduino, etc. So with that, we have the, let's say, hardware electronics. Of course, you will need some end stops. The end stops are just basic switches that they tell you when the circuit is closed or not. So when you home, the machine goes to the origin and touches this button. In the moment it touches this button, it confirms that has reached that position, because the machine doesn't know where it is. When you are controlling the machine knows now where it is. How? Because it's calculating everything based on the amount of rotational move. But the first time you connect to a machine, it doesn't know where it is. You need to home it. So what the machine does by homing, it doesn't know if it's in the space, it's in your backyard, or wherever the machine it is. Doesn't know where the hell he's doing at all. So when you home the machine, you can define on the firmware, you need to move to the left until you touch a button. And it's the only condition the machine has. When you home, it's a super basic instruction. Rotate the motor left or right, depends on how you set up your machine, until you touch a button. If you touch the button, that is 0. And from that absolute coordinate, now you can calculate the amount of movements that you want to go, so you can reach this position. But without initial homing, the machine doesn't know where they are. That is for open loop machine control. Open loop systems, that is machines that they don't have feedback. It means the Arduino is sending instructions to the motors and is trusting that everything is working well in the hardware part. It's trusting that the system is correctly assembled. But let's say, for example, Benji jumps into the machine and stops the machine manually. It's stronger than the machine and will stop it. The Arduino or the whatever control board is actually thinking that it's moving, but it's not in the good position. Open loop machines, they don't have any kind of sensing back. They cannot sense where they are. Industrially, you want to use closed loop control systems. Where?
What is the Edu? What is the? I'm not sure if it's called killer code or something that you have with the Kraken.
Where?
Killer something. I thought, because I saw it yesterday when I was struggling with the problem, but I thought it was like an action that decided like, hey, stop the machine because something is not going good. Do you have anything coded in there?
We can do it in Repetier. In here, I don't know. Actually, I don't know these things.
I heard something that was saying like killer code or
yeah, like kill with the brackets, like it's a function to kill the machine because it detected something was going wrong or something.
But I think that is the Marlin function that detects that something is going on and kills or halts the machine and relaunches it.
Kill Marlin.
Poor thing.
Straight away.
Kill halted is usually the command. I don't know.
Yeah, it was something like this.
Okay, wait.
Please don't stop my drawing. Oh.
Kill it.
Kill or stop. Unconditional stop.
What you had before in the Google, it seemed like that was the error we got yesterday.
Yeah, it's unconditional stop. You have several types actually. Depends if you want to actually freeze the system or not. Cancel current motion mode. Actually, G-code commands are super huge list. I don't know all of them.
I don't think that was I think it was an error setting, like probably something else than Martin, because it was, the machine was hitting the sides.
Emergency stop.
Yeah, I think it was like something like shit's going down.
M112 emergency stop, I think. M112.
Yeah. Okay. Yeah, you need to run this one and after M1999. It's nice. 112 is the emergency numbers. Can I send it now? Wow. So I'm lost. What I was saying? Closed loop. So usually open loops, you have the control board sending to the drivers and the motor is moving, but it's not giving any feedback to the position. Let's say the machine is blind. Some kind of control systems, they allow feedback and we call them closed loop. So basically the motor measures the amount of movement produced and sends the information back to the controller. And in case there is a mismatch between the amount of movement that you have sent and the amount of movement that you have really done, they correct it. There is a really nice example of this to show you. That is, I like to show you things in videos in YouTube. Really easy. SB42 closed loop. Yeah. So for example, this will be the difference between open system and a closed system. Let's see. It's around here. No, it's not this one. I hate Zoom, so many windows around the screen. Here, this one. So let's say, for example, this is an open loop control motion system that, for example, if it hits something and it doesn't reach the proper position, let's say you hit, it loses the position. The control board doesn't know exactly where it is. So it keeps sending commands as if nothing had happened, but there is a big offset between the position that it should be and the real one. On closed motion systems, that doesn't happen because the motor is counting the amount of movement and also the position. So if you see it hits, it corrects back. It counteracts the loose steps. And actually all the big machines, sorry, so much noise. Wait, I close the window. All the big machines, or at least the good ones, for example, the SRM is telling you the position on the firmware, no? You remember the SRM control system, like the small milling machine, it was telling the coordinates. Because the motors, some steppers, closed loop, you don't especially use a stepper, you use what is called a servo motor, that is slightly more complex. They have a control board behind the motor that is measuring the magnetance of the coils to measure with a magnetic encoder or linear encoder the amount of rotations produced. So let's say the control board is telling the control this servo motor. You have to rotate 20 degrees. And somehow the motor rotates 21 because you push too much or hit something or is getting a back error mistake. So this 1 degree more of movement has been measured by the encoder and is sending information back to the microcontroller. So the microcontroller will know that it needs to send 1 degree less to really get to the proper position. So that is closed loop. And of course, these systems are much more expensive than open loops, but they give great accuracy. And actually,
would they take into account the backlash you were talking about earlier, how it would start moving, but it wouldn't, it would count the rotation, but if the gear isn't tight?
It will, yeah, it will accommodate, it will sense on the motor, but it will not know what happened on the gear.
Okay.
Unless that system also exists. And for example, they use laser guides to measure the accuracy between the top of the machines. But that is for really, really high professional grade ones, usually.
Could they detect if there was it turned, but there was no torque because it was in the emptiness, so it knows it wasn't moving?
Yeah, usually those kind of machines, they already prevent by designing well the hardware that the backlash doesn't exist. For example, there is a really nice video on PID control. I think I already showed you, but PID.
Yeah, with the thing correcting.
I think you already showed you that.
Yeah.
So that's what, for example, the PID control systems can be embedded with closed loop system to actually prevent these kind of things happening on time and prevent back and have better correction. I don't know. I think it was in one of the classes. I'm pretty sure I showed you.
Yes, I think in the
output devices. Yeah.
Output devices, no?
Yeah, it was the not
output devices. Yeah, for example, this is a small DC motor with an encoder. With this, you will be able to do a closed loop system. Creo que no lo puse en la clase. No. Qué rabia. Bueno, ya lo buscaré. Well, it's not a big deal, but I want you to understand that there is closed loop and open loop. And of course, that influences the complete price of the machine, but also the accuracy. When you want to have open loop versus closed loop system, depends on how dangerous is the machine or the system that you're assembling. For example, if the CNC that is cutting aluminum loses one step, you can screw up everything really fast. That is really dangerous. So in those cases, for example, most of the CNCs, or the good ones at least, are closed loop, and you want to have a closed loop system. With 3D printers, that increases the cost so much compared. Yes, you mess up a print, but the cost quality of the system of the prints are really low. So actually, you don't care about losing steps, and it's something that you can avoid just by making a good setup in the hardware one. What happens, for example, when you want to control more complex systems? For example, one thing that is a big constraint in the Arduino is the memory. It's not really big. It doesn't have too many things to connect. For example, you may recognize this. These 3D printers, they usually don't use Arduino Uno. They use Megas. Why? Because you need to control more motors. X, Y, Z, plus an extruder, plus temperature sensors, plus heating systems, plus MOSFETs, plus relays, plus a fancy interface like a screen. So Arduino Uno doesn't have enough ports, doesn't have enough pins, and doesn't have enough memory. So they jump up to, for example, Arduino Mega. And the CNC shield for the Mega is not called CNC shield, it's called RAMS, because it's designed mostly for 3D printers, because it's the kind of system that needs that amount of pinouts. And they have the MOSFETs to control high power drain devices already in the board. This is kind of, I'm talking about open source. You can find the same, for example, MakerBase, a lot of providers, they sell custom boards that they have the same, but as one piece layout. It's one board that does the same. Instead of having Arduino Mega plus a shield, just because this is cheaper to manufacture for them. Obviously, there are small differences because each manufacturer enables more pins or less pins, or better MOSFETs or worse MOSFETs, etc. But they are basically the same. Now, this is all talking about 8 bits. ¿Cómo se llama, Óscar? ¿Cómo se llama la placa que controla la de Miquel? ¿Qué es la pepina esta?
No lo sé. No lo sé. Trigorila puede ser.
No.
No sé cuál es.
So right now, for example, before we explain that depends how fast you send the commands and how fast you can do, and the delay between the movements of the motor. You remember X, Y, and Z. We are sending one by one because at the end it's a set of instructions. Your clock frequency will determine the small difference in time between sending the instruction between X and Y. Theoretically, and it should do at the same time, but we are not multi-threading. We are reading instructions. So actually, first, if you set a G1 command that has X, Y, and Z, it's going to activate them by order, X, Y, and Z. So there is a small, really small delay. And the delay is going to be determined by your clock frequency. So right now, there is a big move to jump to 32-bit control boards. Why? Because you have much more speed. That's easy. You have much more clock frequency. And by that, you can reduce the time difference between sending commands to the X, to the Y, and to the Z. So there's going to the reduced millisecond time is going to be reduced from 0.1 millisecond to 0.01 millisecond, because I think the duet Wi-Fi has a clock frequency of 160,000. So it's 20 times faster than an 8-bit controller. So right now, there is that will determine, let's say, the quality of the. I'm talking to you about 3D printers because I think it's something that you can relate and you can see the examples clearly. But that implies for every system. For example, 3D printing, the artifacts set. Yeah, these kind of things could happen. First, hardware-related issues, that is the 99% of times thing, but also because you have a system that is the 8-bit cannot process the data that fast. For example, when you high-speed print, you need to send commands really fast. And that makes a small delay between the motor coordinates producing this kind of artifacts. And this is on 3D printing. That is also applied for CNC milling or etc. Because right now we have reached really good systems that you can print at 600 millimeters per second. So usually at the lab, usually print around 30 millimeters per second. This is not really fast, actually. This is around 150. But professional grade printers can reach easily 600 millimeters per second. It's half meter per second. They can move really fast. That means you need to process a lot of instructions really fast. the amount of data it needs to process per second is huge. So increasing the clock frequency improves the delays between the different motors and reduce the whole artifacts and mismatching between the movements of the motors.
And the big deal is also how to extrude the material.
Sorry?
The big deal with that kind of speed is also how to extrude the material, no? To get perfect consistency at that speed.
When you want to print at that speed, you have a lot of things. One is you want to, have you noticed the Ultimaker? How heavy it is?
Yeah.
And actually the printing part is really light. It's a printer designed to be able to print at higher speed than usual. Because if you are moving something really fast, you want to have a really sturdy frame that weights. And actually machines that are doing either really heavy stuff machining or they have to be really fast, they are also usually really heavy because they need to hold themselves without vibrations. And vibration is something that kills any kind of accuracy for any kind of process. You always want to avoid vibrations. So you want to have a sturdy frame. Second, you want to have the lightest print head or like tooling head as possible. So you can move it faster, so you have less inertia. Third one in 3D printing will be, I need to print that amount of plastic. I want to be able to melt that amount of plastic. That is something that could be easily solved because there are solutions. For example, Super Volcano, Potent. Is 3 times longer than a normal printing head, just the melting zone. So for example, if you go to Volcano Hot 10, they have like charts of the maximum flow rate that you can reach with this kind of systems. I think, yeah, here, for example, can print 11 times more amount of volume of print in the same amount of time. That's a lot. So melting the plastic is not a big deal. It's about, for example, and for high-speed machining will depend on your motor. A higher torque motor with a higher RPM count. So usually the problem is not on the tool and design to produce that system, but about on the mechatronics. How you produce that movement without vibrations. And without, especially something that is backlash. Benjamin, for example, if you have a belt, that is something they usually use for making fast movements. Because it's light, you have a problem. The belt, when you change the direction, straightens in both directions and elongates and deflects back. First, you can break the belt easily. So you need reinforced belts, usually with del rim, like steel, sometimes carbon fiber inside, etc. Second, the belt is going to have backlash, a lot of backlash, and especially high speed, that increases a lot. So in those cases, you don't want to use belts, or you want to increase and over-dimensionate the belt for the load, not on the maximum strength of the belt, but on the elongation amount based on the distance. Of course, Kraken doesn't think about anything of this. For example, this is a RAMS connection board. And actually, for the Kraken, as we want to, actually Kraken has 1 servo right now, but we are able to connect 5 servos and 3 motors and whatever you want. What we do is start already with a RAMS. So we are able to connect as many things as we want in the future. Okay, what is inside here? What is the control of this and how can we control this kind of things? For control system firmware, there's a lot of types, and you can actually see Repetier, Smoothie, Wear versus ERBL. There is a here. There is a lot of types of firmware to control, and actually what is the firmware? Is the thing that interprets the commands you are sending and translates it into movement. It's what it says, how you need to accelerate and clear all drawing. Yes, because if you want to move from here to here, okay, you say move. That in the real world is not like that. Doesn't happen. As any motion, this is the time, and this is the speed. You need to accelerate, reach the speed that you set it up, and decelerate back. Also, to do what? Reduce backlash. This is also done on how you interpret your data and how you accelerate your motors. Of course, you can have really low backlash if you have accelerating curve like this. What happened? In case if you 3D print, something that you need to change is, in here, I need to extrude less, and at the same time, I'm increasing the speed, I need to extrude at higher speed to accommodate so I have the same flow of material. If you get the same flow, but a different speed, you will get a print that it will be like this: fat, thin, fat, for example. So this kind of things is what the firmware controls, and depends on what you want to do, there are options. The more standard ones are, I stopped sharing my screen, sorry. The standard ones are Marlin, that is a firmware control whose main purpose is 3D printing. That means has a lot of back coding, thinking on flow control, flow characteristics, enable different things, like for example, multicolor print, aka multi-tool printing, or for CNC, usually you use GRBR. I never know how to translate this, like it's GB. ¿Es esto? No, no es esto. I always mismatch the names. GRBL, CNC controller. So this is the standard for, let's say, open source industry. Of course, Marlin right now has a fancier page, has a fancier documentation. Let's say everything is easy because it has a big, really huge community on 3D printing. CNC is still something more on garage, let's say, or enthusiasts, not that amateur. Marlin has a really good backend code and lot of support. GRBL has a lot of support, but you need to work harder to make it work. But why to choose GRBR against Marlin? First, you want to have a sturdier setup. Let's say a code that always works, has been improved and cannot fail. When you want to have those systems in a laser or a CNC, because a mistake or a, let's say, a firmware freezing because an error in the syntax will screw up everything so fast and so badly. So GRBR always has been released with a lot of beta tests and prove that there is no mistakes, and let's say has a simpler syntax in the code and how the firmware is assembled to produce more robustness. It means it's a much more robust firmware. Also, one of the main things of using GRBR is has ensured protocols that are safer to use in the speed translation and the data communication to ensure you don't have missing steps or missing mismatch of lines of data. It means you are not be able to lose a G-code line. Meanwhile, Marlin, it can happen. It doesn't mean that it will happen. It's weird, but it means error talking wise, GRBR is much more robust. Also, GRBR curve of acceleration and speed treatment are better because in Marlin, in general, all the ecosystem is designed along the printhead. That means the important is the flow rate of the plastic extrusion and the movement. In GRBR is the opposite. Is what it prioritizes is the motion system, how to move properly X, Y, and Z. So actually, one of the things that the GRBR does in the back end is calculate first at the highest clock speed the motion systems, the motions that it needs to produce. So actually, the motion in GRBR is theoretically smoother. Like I have used both a lot, and I have not feel the difference. Like I have to be honest. But when I like looking at the code, looking at the people that is building it and contributing, they always ensure like safety, priority, and accuracy amongst options and multi-purposing as Marlin. Marlin enables features like crazy features, lot of millions of features, and you have a lot of people contributing. That means like it's a contributed system. The same is in GitLab or GitHub. I think both are in GitHub. You have a lot of pushes, and not all the times they are working, and they are a lot in beta, and they never finish development. In GRBR, actually, most of the things that are being developed with a community that support it and is always working. Let's say it's a much sturdy system. At the same time, it's a much less capable system. With GRBR, for example, only 2 years ago, they introduced servo support. Something as simple as servo support to raise up a proving tool. Marlin, this was done since the first day of Marlin because they want to have that for like automatic set leveling. So there is no one better than the other one, but calculation wise and accuracy motion wise, GRBR is better. Another thing is GRBR is not meant to use a standalone. It means it's compiled to be used always connected to a computer. Why? Against thinking about safety. Let's say you have Arduino Mega reading an SD card. SD card can get corrupted easily, happens. Like for example, I print a lot. I have already corrupted this year 3 SD cards. Can get mistakes while reading an SD card. It's not that a reliable system as connecting with a control interface to a computer that process all the decodes and send it to the board. So actually the board makes less work, needs to process less amount of data, and only focus on translating the movements. Meanwhile, Marlin will do much more work and also process the movements. So GRBR is always thought to be programmed or to be flashed onto a 80 mega, and now they jump also onto 32 bits, I think. Simple board, let's say an Arduino Uno. You don't need the manufacturer's features, and what you want to think is about robustness. So Arduino Uno is ideal for that. It doesn't mean that Uno is better than Mega, no. But for just clean motion control, Arduino is enough. You can do it with a Mega. Yes, actually there are ports of GRBR to be used with Mega, but there are not that many supporters because not the people don't find why I will waste my money on a Mega when an Uno does the same, and I don't need that many pins outputs. Because for example, 20 pins of the Arduino Mega just goes for an LCD screen control. In a Uno, you don't need it. You are connecting with a laptop that does all the cam and the interface. Marlin, on the other hand, supports a lot of boards, 32, 8 bits, I think also 16, I'm not sure, ADR, ARM type of boards. So, for example, in this case, the 6-pack milling machine is going to be based on GRBR. We want to build a really sturdy milling machine, simple as possible. So also we can reduce the price of the controller much better. We can have better motion control. So GRBR for the 6-pack milling machine. And a guy just ported it to the ESP32, so we got really lucky. It's perfect for control of this. If we will have not used a Arduino, we will have made our own Arduino control board and for this with GRBR. It's much sturdy and works really well. For example, the Kraken is the opposite. We want to have like everything, or at least be able to use everything. So we went for Marlin. That's, let's say, that difference. Both, I think I have Marlin around here. So let me check. I think it's in fabricatable tools. I have a copy of Marlin. Yeah, firmware raw Marlin. Let's extract. Oh, I will copy this one. I will start it here. Extract firmware to Marlin. Yes. So Pablo before was asking about this. For example, this is the whole firmware of Marlin. You see, this is all files that is just for configuration of Marlin. Actually, this is almost 200 files of different things. For example, one kind of LCD, another type of LCD, another type of LCD, another type of LCD. This is just for the characters, for all the translation of all the languages. GRBL just comes in English. Okay, literally. Sorry for the expression, but it's like that. Utility, watchdog, to actually save time or save electricity wise on when you are printing, etc. So lot of termistor tables. We don't need that many of that stuff for controlling just an XY Cartesian motion. But this one is meant for rule them all. Marlin is to rule them all, more or less. You need it because you need to be able. Of course, when you open it, this is all, let's say, internal libraries that Marlin is using. So let's open it and let's see what is inside.
Edu, and can you clean those libraries or the firmware only with what you need?
Yes, you can do it, but you will need to erase the calling libraries from the different parts of the code.
So it doesn't work the work?
Yeah,
doing it?
You can erase them, but you will, why, sorry, I need to change the name, 1 second. Sorry, I will answer you in 1 second, okay?
Don't worry, don't worry.
Rename, I hate this of the Arduino.
If you erase the package, it will be messy on the next update or something.
Yeah, also will be really messy in the next update, for sure. One of the main reasons, for example, that actually Arduino Uno is able, in the limit, to control a 3D printer. Has enough pins, but not to an LCD screen. And especially when you have reached this level of code, it doesn't fit. Doesn't have enough memory. It's too huge. For example, GRBL, they always think about the total sketch weight. They always try to lighten and take away unnecessary stuff. So for example, you have the just open file that is telling you where is all the information, and you have all the coding. For example, this is for mesh validation. Actually, this is some things that I really don't know why they exist. LCD conditioner, something useful. This is configuration for the LCD, standard, the LCD, the unit panel, and you say they have set up all the kind of standard screens of the market. Luckily, both GRBR and Marlin, you just go to config. That's it. You can define the version, for example, you can choose which kind of printer. For example, here, you can set up the name when it boots, what names is showing on the screen, what port are you connecting, the baud rate you want to talk with your machine, the board that you are using. Really important, just to do what? The pinouts. So actually, for example, Marlin is not meant to you for change the pin configuration. Is just to define your board. So here you define the motherboard that you are using. For example, GRBR has all the pins that you can literally change the name of the pins manually. So it's easier if you want to make your own custom system. So if in case your motherboard doesn't exist because you fabricate your own, you will need to go and look for your board, open that file or make a copy, modify the board files, and upload it again. So for example, so annoying, so many bad apps. Oh my God. Actually, where are the boards? Well, you can get the idea. It's just a simple file with all the pins out. For example, if you have 1 or 2 extruders, what is the calculation of what? Have you noticed that before asking what is the step translation of the motors, is asking about your filament? Because everything is based on the filament. So actually with this, it will calculate the amount of extrusion that will need to compensate. extrusion multipliers, how many students you want or you have, etc. For example, we have here, sorry, chat, let's see, what do we have? Oh, sorry, didn't know the class. Well, I will.
No, don't worry. Sorry for living in the half.
No, don't worry.
We'll see the recording of the last minutes.
How many?
I think it's already like 2:15.
Yeah, 2:12, 2:15.
And let's talk.
3 minutes. For example, maximum limits
well,
of your,
I'll stay then.
The maximum limits of your machine, the minimum temperature, and something that is funny, but you need to really scroll down is actually what kind of steps you have. That is the most important one. Like how many steps you need to do 1 millimeter of movement, and it's just really low. So for the X, 80 steps will produce a 1 millimeter movement. 80 steps of the stepper driver. And this is the steps for the extruder, for the Z, and this is one for the extruder. The maximum or default feed rates, actually, this is the default, the maximum speed that the machine can reach. You can limit it. Actually, in the Kraken, the acceleration and the feed rate, we have put it really low. Accelerations, jerk, different types, and options, and thousands of options. One of the main will be, for example, travel limits. How big is your machine? Basically. With this, you set up that the machine cannot move farther than, in the case of the Kraken, 700 millimeters. If you don't set up this number properly, the machine could get out of the limits and will try to break itself. So luckily, both GRBR and Marlin have the config file. That is when you want to enable everything. And usually this file is quite long. If you want to configure it purely, it takes a few hours just to go over everything. Because, for example, I don't even know what this is. Extra features, because there is no extra features. Temperature status LED, etc. So more or less, that's it. And Kraken uses Marlin. And also because Marlin is a sea animal, we also use Kraken because it's also a sea animal. Okay, questions? I know I went really fast, but
okay. So we talked about networks, G-code, machines, mechanical design. I don't know. Probably this was like a FAB Academy, half FAB Academy in 4 hours. Do you have any questions?
I have questions about.
Okay.
No, I mean it's a lot of things, and I want to have lunch.
Get used to, because next week is machine design.
Where we won't design any machines.
Huh?
Where we won't design any machines.
Actually, you're gonna start with the 6-pack milling machine. This is something that you need to do, yes or yes.
But not designed by us, though.
No. Wait.
Machine building week.
No. You cannot build a machine just as it is. We have provided you a basic machine design. Now it's up to you to modify. You want
Actually,
to
normally
laser, do it. You want to put a servo to rotate the bed, for example, do it. You might need
we have to talk about this a little bit, because this is normally a group assignment. It's not an individual assignment. And actually, we haven't decided exactly how we're going to do it in Barcelona, but I think the best is that at least we form 2 or 3 groups in FAB Academy, and that you set up we will provide you with a GitLab repository for the machine, and we will create it probably with the base files and something. And from then you start editing. So we'll see. I think that's what we're going to end up doing, but it's not going to be an individual assignment. You have to also learn how to collaborate in this type of projects. And actually, you will also have to create a website for the machine. So not only the design, but a website for it where you explain how it was done, you put a video of it working and everything. So even if we provide you with a base design, it's not done. So
cool.
Don't worry, you have work to do.
Good. Antoine.
Thank you, guys.
Yeah.
Okay.
Gracias, chicos. Que estén muy bien.
Igualmente.
Hi.
Hello,
There is
Antoine.
my drawing.